Sample exam number 2. Answers. Problem 1. Determine the domain and range of the following function. F of x equaling 1 over rad x squared minus 2x minus 3. First, let's determine the domain of this function. So, we do not want to divide by 0. Nor do I of a negative number. Therefore, what's inside the square root must be positive. Factor x minus 3 times x plus 1 is greater than 0. So now this is in factored standard form. So let's determine my critical numbers in order to solve this inequality. And so to determine my critical numbers, I'll just set each factor to 0 and solve for x. First off, let me insert an extra page here. So let me add 3 to both sides of my equation. X is equal to 3. Let me subtract 1 from both sides of my equation. So x is equal to negative 1. Now let me place these critical numbers on my number line. And let's determine the sign of this inequality in each of these subintervals determined by this.
Question?
Yes, question. Mm-hmm.
No, that.
Okay. Where was it?
So let's determine the sign of my inequality in each of these subintervals. So take a number greater than 3. Positive times positive is positive. Take a number between negative 1 and 3, let's say 0. Negative times positive is negative. Take a number less than negative 1, say negative 2. Negative times negative is positive. So we wish for these, okay. 1 second. I wish for this to be greater than 0, so I will not fill in either of these critical numbers. And then I want this to be 0, so it'll be positive. Let's fill in where it says plus, and that is my answer. And then let me see what the question is. Chat. Okay. So let me see this question. Is this being recorded? Yes, it is. It is being recorded. So it'll be recorded, and you can then click on it to listen to the recording just by going back to virtually the same place that you came here. I'll then also put it in the sample exams. I'll place it there so you can also listen to the whole thing, because we'll probably only do half today and half tomorrow. So the domain of my function is the union of these open intervals from negative infinity to negative 1 and from 3 to infinity. So that is the domain of my function. So now let's determine the range of my function. It's okay, let's determine the range of my function. I'll do it sort of 2 ways. So notice that this is a positive square root. So we can't have that the y values are negative. And this is also a rational function, so there's no way that this can be equal to 0. So the range is actually the set of all y values greater than 0. But let me do it a little bit cleaner. So I have that in this region here. So notice that if I'm in my domain, so if x is in the domain, then the y values here, well, then this inequality will hold less than infinity. Since we determined that, we determined right here that it was greater than 0 in this region. So now the square root takes positive quantities to positive quantities. It's injective, always increasing. And so I have taking the square root of everything, that the square root of x squared minus 2x minus 3 is between 0 and infinity. And so now let's take the reciprocal. So if I take the reciprocal of this quantity, then I'll bring this over here. The reciprocal of this is infinity. Reciprocal of this is 0. And so I have that all of my y values are between 0 and infinity. Therefore, the range of my function is just the open interval from 0 to infinity. And that is my answer. Simplify the difference quotient for the following function: f of x equaling 1 over x. So first off, the difference quotient is defined as f of x plus h minus f of x over h. Okay, so we want to find the difference quotient when f is equal to 1 over x. So this is equal to 1 over, wherever I see an x in the formula for f, I'll replace x by x plus h minus f of x, which we said was 1 over x, all divided by h. Now we want to simplify this. So simplifying this, I want to somehow write this so that there's no h in the denominator, that there's no single h by itself in the denominator. So first off, let me add these two quantities. In order to add two fractions, I have to find a common denominator. And then let's divide by h. So let me just write it in this form. And so to get a common denominator, well, the common denominator in this case is just x times x plus h. Okay. And so let's multiply and divide by x, multiply and divide by x plus h. Okay. And so I get x and then x plus h in a second. Now, dividing by h is the same as multiplying. And so now let's simplify this. So this is x times x plus h is my common denominator. And let's subtract x minus h. I'll distribute the minus sign inside the numerator. So times 1 over h. Let me cancel the x's. And so this is equal to minus h over x plus h times 1 over h. The h's cancel. Good, that's what I wanted. And so I get a negative 1 over x plus h. And that is your answer. Let me do problem number 3. A guided missile is propelled from the origin of a coordinate system with the x-axis along the ground and the y-axis vertical. Its path or trajectory is given by this equation. Y equals 4x maximum height. Well, first thing to notice is that this equation here is quadratic. So y equaling negative 16x squared plus 400x is quadratic. And we know that the maximum, well, so this is quadratic. And let's say it's in the quadratic is in the form ax squared plus bx plus c. The general way of writing, general form for the quadratic. Then I know that if a, which in this case is negative 16, is less than 0, then, let's see if I can feel good. Then I have that this is going down. And I know that the maximum occurs at the vertex. So what I have to do is I have to determine the vertex. So let's actually determine the axis of symmetry. That will be easier in this case, because there's a nice formula for the axis symmetry. Axis symmetry is just x equals negative b over 2a. Okay, so in this case, I have that x is equal to negative. Well, b in this case is 400. A in this case is negative 16, and you get positive 200 over 16, which is just 25 over 2. If I redo, okay, and let's add an extra page here. So 25 over 2. So I found the x coordinate of the vertex. So the axis symmetry gives me the x coordinate of my vertex. So now let's find the vertex. To find the vertex, I just substitute for x into the equation. So negative 16x, 25 over 2 squared, plus 400x, 25 over 2. And let's simplify this. So this is equal to 2 squared is 4. And so I have negative, well, so negative 16 divided by 4 is a negative 4 times 25 squared, plus cancel, 400 divided by 2 is 200 times 25. 100. 200 times 25 is 5,000. Minus 2,500 is 2,500. So the maximum height is 2,500 feet, which will occur after 12.5 seconds. Let me do problem number 4. Sketch the graph of the following function. So let me determine the x-intercepts. Actually, let me determine the y-intercept first. I can determine the y-intercept by setting x equal to 0 and solving for y. Well, 0 times anything is just 0. So the x-intercept, y-intercept is at the origin. Next, let's determine the x-intercepts. So I can determine the x-intercepts by just setting y to 0 and solving for x. Since this is a polynomial over the integers, an integral domain, then this polynomial is, this is also an integral domain. So therefore, if the product is 0, then at least one of the factors is 0. So by the 0 factor property, I have that x is 0, x plus 1 is 0, x minus 3 is 0, or x minus 2 is 0. Subtract 1 from both sides, add 3 to both sides, add 2 to both sides. Okay, so we have the following x-intercepts. 4 of them. we have that each of these roots are simple roots. So each of these are simple roots, meaning the multiplicity is 1. Therefore, that means that these will cross the x-axis in a fashion that looks nearly linear. And so these will cross the x-axis. So each of these roots so y at each of these roots crosses the x-axis in a linear fashion, a polynomial of degree 1. Okay. Next, since this is a polynomial of degree 4, so I have that this here has degree 4. So, or maybe I'll say degree of this polynomial is 4, which is even and since the leading order coefficient is greater than 0, then that means we go up into the first and second quadrants. So now let's just sketch the graph of this. So we have roots at, well, here, let's do 1, 2. Okay. So let's just put some tick marks here. We have roots at 0, -1, 2, 3, and then that's it. Let me just finish off these tick marks so it looks sort of nice. Okay, so I start off, eventually I go off into the first quadrant, and so I look linear, go through this, go through that, and wait 1 second, I just sort of, I tried, but it didn't quite work. My pen slipped. Again, it slipped. Okay, let's see if I can do this without slipping. Well, it slipped again, but I'm getting sick and tired of trying. It's just too, okay. So this is equal to y is equal to f of x. X x plus 1, x minus 3, x minus 2. So that's a graph of our function. And notice that when it crosses, it more or less looks like a line at each of these. Let me do problem number 5. I want to sketch the graph of the following function. F of x is equal to the greatest lower bound, the greatest integer, less than x plus 2. So let's do this. So it this is going to just look like a step function. Actually, it's a translated step function. So let's just sketch the graph of this. Okay. So let's do this. Just do my tick marks. Okay, good enough. So let's start out. Let's start out just at 0. We'll draw it for 0, 1, 0 for things like greater than 0, and then I'll start to draw it for things less than 0. So at 0, well, 0 plus 2 is 2. So it's here at 2. If you're at a half, you're 2.5, so you're still at 2. You're still at 2 till you get up to 1. Then at 1, you jump up to 3. And then at 2, you're going to jump up to 4. And you keep doing this. Okay. Now, at -1, you're at 1. At negative fractions, you're still at 1. At 0, you jump up to 2. So it looks like this. At -2, you're at 0. And you keep looking like this till you get up to -1, where you jump up to 1. And the pattern continues. And so this is the graph of y equaling the greatest integer less than x plus 2. Let me do problem number 6. Sketch the graph of the following function. So first off, let me rewrite this as 1/2 rad x plus 5 minus 2. I like to write y rather than f of x. Now let's bring the 2 to the other side of my equation. And so I have y plus 2 is equal to 1/2 rad x plus 5. So now I can see that this is a translation. Oh, wait. Aha, okay. That this was a translation of y equaling 1/2 rad x where I am moving 5 units in the negative x direction. So left by 5. And I'm moving 2 in the negative y direction. So down. So now let's try to sketch this graph. So now maybe I'll multiply both sides of my, well, maybe I'll just, yeah, let's multiply both sides of my equation here by 2. So I have 2y equals rad x. And so this is a scaling. So I'm going to compress the y-axis by a factor of 2. So I'm squeezing this so it's half of its original size for the graph of y equaling rad x, which just looks like a parabola toppled on its side. We can see that because it's an inverse function of y equal x squared. So let's sketch a graph of this. So I'm going to,
Professor,
yes, question.
really quick, how did you get 2y equals rad x?
Oh, multiply both sides of this equation by 2.
But before that equation, what did you have?
Oh, to go from here to here.
Yes. Okay.
Yes, okay, sorry about that.
No problem. Thank you.
Okay, so so instead of writing, I'm replacing, it's a transformation. So instead of writing y plus 2, I'm going to write y. In reality, these are new variables, like y prime and x primes. I just don't write them. So I'm going to replace y by y plus 2 by y. That I take the graph and translate it down by 2 units. And I'm going to replace x plus 5 by x. When I do that, I'm going to move the graph by 5 units to the left. Okay, that's just translation of question. Yes.
I have a question.
Mhm.
Do we have to rewrite the equation? Because the way I was taught it before is that we're just looking at it, you can just write down like left by 5 and right and down by 2.
In this case, in college algebra, you actually want to do the translations and scalings. So when we did this in Math 125, we didn't use, well, so in 115. In 115, we didn't use any translations or anything of that sort. You can graph it just by saying, okay, this is how the sketch looks like. But here in 245, we want you to do the translations and scalings. So it's really because we want to be sure you know how to do those. It's not necessarily that you have to do it in order to sketch the graph. I myself probably don't actually do. I just graph it. But you, for an exam, you would need to do this. You would need to do the scalings, the reflections, and the translations.
What if we explain it, like how you did with the words?
You'd have to do translations and compressions. So that's the important part of sketching the graph. Okay. So the important part is that we know that you know how to translate and scale and reflect. So those are the important parts of the sketching. Okay. Okay. So, I didn't do this yet. Okay. So let's do this. Oops. X, Y. So let's put some tick marks. I'm not going to really use them a lot, but let's at least put some tick marks here. So after I've done all my tick marks, I'll first sketch the graph of the last thing that we did, which I think was the square root of x. So, and let me change my color, the square root of x. So let's sketch the graph of the square root of x as best I can do. So this is the graph of rad x. And now what I want to do here is I want to compress the x-axis, the y-axis by a factor of 2. So I'm going to be compressing this y-axis here by a factor of 2. So when you do that, so when you're compressing down here, you can see that you're going to be squashing this down so that it's now this here goes down to being half its height, its original height. So every point here, nothing changes here, but this is squeezed down to half its height. So it's going to look something like half its height. Something like this, more or less. Y equaling 1/2 rad x. Okay. And now I want to do a translation. So let's do a translation. So I'm going to go 5 units to the left, and I'm going to go 2 units down. Okay. So let's do that. So this goes over 1, 2, 3, 4, 5, and down 2. So this graph here goes over here, down 5, over 5, down 2. And it's going to be relatively short. I think I made it too steep. Not bad. Copy. Paste it. Oh, okay. There. And so there it is. Okay, good. That looks better because it's just all I've done is just moved it. So this is the graph of your function. So now this is y equals 1/2 rad x plus 5 minus 2. Okay. And that's what the graph looks like. Something more or less like that. Okay.
Do we just draw the final graph, or do we draw?
No, you would need to do all of the you need to do the original, all the intermediate graphs in between, and you have to tell me how they are transformed. So you need the original graph and then each of the transformations. Okay, because that's the crucial thing that we're looking at. Let me do problem number 7. Sketch the graph of the following function. Okay, so first let's see, can I even simplify this? So let's try to simplify f of x. So let's see if I can factor -2x cubed plus 3x squared minus 2x plus 1. Well, first let's see if there are any rational roots. And so let's use the rational root theorem. And so p here, factors of 1, q, factors of 2, 1 and 2. The possible rational roots. So the possible rational roots are, divide 1 by 1, divide 1 by 2. So there are these 4 possible rational roots. Let's see if I can factor this. Let's try 1. And so negative 2, x cubed, 3x squared, negative 2x plus 1. Okay, so let's factor this. Drop down the negative 2 times 1 is negative 2, plus 3 is 1. Good. So I get a 1. Minus 2 is negative 1, plus 1 is 0. Okay, so that says that negative 2x cubed plus 3x squared minus 2x plus 1 is equal to x minus 1 times negative 2x squared plus x minus 1. And actually, that does not seem to factor over the reals. Obviously, you'll have a complex root, but we're going to be graphing, so I don't care about complex roots. I only want to look at this over R. So let's look at my discriminant. So let's look at my discriminant. So use your discriminant. And so D equals B squared minus 4AC. And so my discriminant is B squared minus 4AC. That's going to be 4 plus 4, which is 8, which is greater than 0. So therefore, I know that this does not factor. Oh, this is positive 8. Oh, wait, one thinking second. It would be nice if I actually plugged in to the correct polynomial. 1 second. B is 1. I'm sorry, I was looking at I wasn't looking at the correct polynomial. B is 1 minus 4A is negative 2 and C is negative 1. So this is 1 minus 8, which is negative 7, which is less than 0. And so since my discriminant is less than 0, this implies that this polynomial is irreducible. Over the reals. Okay, good. So now let's get back to the original problem. So f of x was equal to, well, x minus 1 times minus 2x squared, minus 2x squared plus x minus 1 over x squared minus 1. But I can factor x squared minus 1. as x minus 1, x plus 1. Now, I can simplify this, but we have to be a little bit careful because by doing this cancellation, I create a hole. So I'm going to have to check if I have a hole. So f of x is equal to negative 2x squared plus x minus 1 over x plus 1. This is so long as x is not equal to 1. Because we did isolation here. So this changed the domain of my function. It might have changed the domain of my function. It does not necessarily change the domain of my function, but it could have. In which case, we might have a hole. So we better check to see if we have a hole. When x equals 1. So, well, that sounds like I know I have a hole. So check hole when x equals 1. So I'm going to see if there is a hole in my function. So let's do that. Well, let's plug in for x1. And see if my function is defined at 1. So this is going to equal negative 2, 1 minus 1 cancels, so just negative 2 over 1 plus 1, which is 2. And that looks nice. So I have that f of 1 is negative 1. So therefore, there is a hole. So f has a hole at 1, negative 1. So I'm going to have to, as I sketch the graph of this, I'm going to have to place my hole. I'm going to put in a hole. Okay, so let's look at my y-intercept. My y-intercept will probably give me nothing. And so set x equal to 0. And so I get y is equal to negative 1 divided by negative 1 is 1. And so let me add another page here. So I have a y-intercept at 0, 1. Okay. Let's look at x-intercepts. Well, in order to find an x-intercept, I have to set negative 2x squared plus x minus 1 over x plus 1 equal to 0. But the only way that this rational function, rational expression can be 0 is if the numerator is 0. Just multiply both sides of the equation by x plus 1. But I already know that this equation has no real roots. And so no real roots And so that means that there's no x-intercepts. Good. So that means that my function does not cross the x-axis. Okay, good, good. That tells me something at least. Now let's look at some asymptotic behavior. So first, let's look at the vertical asymptote. And so the vertical asymptote is found by setting the denominator to 0, solving for x. So that's my vertical asymptote. Note that it would be wrong to set the denominator to 0 in the original function, because you had to have simplified to check that there were no holes. So when x is 1, it's actually not a asymptote, it's actually a hole. So we know that actually it's a hole at 1. Okay. Now let's find my horizontal asymptotes. Well, I have that, so y is equal to negative 2x squared plus x minus 1 over x plus 1. Well, the degree of the numerator is bigger than the degree of the denominator, so there's no horizontal asymptote. If you try to simplify this, you would see that this first term is not going to give you a constant. It's actually going to give you a negative 2x in this first term. So there is no horizontal asymptote. Because the degree of the numerator see that degree of the numerator is bigger than the degree of the denominator. Okay, so because of that, there's no horizontal asymptote. Okay, so let's try to find some additional asymptotic. A slant asymptote, so first off, let's simplify this. So let's divide, and I'll just divide synthetically. So I have a negative 2x squared plus x minus 1. So I'm just dividing these two polynomials to get a quotient plus a remainder over the divisor. So drop down negative 2 times negative 1 plus 2. 2 plus 1 is 3, times negative 1 is negative 3, minus 1 is negative 4. So that says that y is equal to, right here, y is equal to a negative 2x plus 3 minus 4 over x plus 1. And that is your simplified function. So now we can see that, well, as x goes to infinity, so asymptotic behavior. This last term here just goes off to 0. And so y is asymptotic to negative 2x plus 3. This is also called a slant asymptote or oblique asymptote. And let's look at the asymptotic behavior as x approaches negative 1. So x approaching negative 1 asymptotic behavior. So y will be asymptotic to, well, negative 2 times negative 1 is a positive 2 plus 3 is 5 minus the 4 over x plus 1. And so that is your asymptotic behavior as x approaches negative 1. So let's see if I can sketch the graph here. It's going to be a little squeezed. I'm going to have to, it'll be squeezed no matter what. Let's see if I can do this. Okay, so 2, 1, 2. Okay, let's see if I can squeeze my graph in here. Okay, so I have here y equals negative 2x plus 3. So plus 3. Let's do it in 2x plus 3. Okay, so this is my asymptote, y equaling negative 2x plus 3. And, well, 5 minus 4 times x plus 1 looks something like this. Okay, so actually let me draw a little guide here, which is actually the vertical asymptote. So it looks something like this and like that. Okay, so therefore my graph has to look something like this in this region, something like this over here, has to approach this and this. So it's got to look something, and then at 0 it was negative 1. Okay, so it's got to look something like this. I sort of fell away there. And so this is the y-intercept, and then there was a hole here at x equaling 1, -1, there had a hole. And then it's got to look, I don't know how far it'll go down, but it has to be approach here and then go like that. So this is what the sketch of my function looks like. So this is the graph of y equaling negative 2x cubed plus 3x squared minus 2x plus 1 over x squared minus 1. So that's what the sketch of the graph of this function looks like. Okay. Let me do problem number 8. Oh, sketch the graph of the following function. So another one. So first off, let's find the x-intercept. So set the x plus 1 over x squared, x minus 2 equal to 0. And so the numerator must be 0. So x must equal -1. So I have my x-intercept at -1, 0. Let's find a y-intercept.
Can you go back to what you just wrote? I missed it.
Sure, sure. Okay. I was just finding the x-intercept.
Okay, got it.
And really, all you have to do is set the numerator to 0, since it's a rational function.
Okay.
Let's find the y-intercept. Found by setting x equal to 0. So you go y equals 0 plus 1 over 0 squared times 0 minus 2. And you go, wait a second, I can't divide by 0. And so there's no y-intercept. Okay, good. Let's find the vertical asymptote. So to find the vertical asymptote, you set the denominator to 0 and solve for x. So I have x squared equals 0, or x minus 2 is 0. So x is 0, or x equals 2. So those are my vertical asymptotes. Let's try to find my horizontal asymptote, which will actually be nice. And so to find my horizontal asymptote, which is really the asymptotic behavior as x goes to infinity. That's really all we're looking at. And so this is just y is equal to x plus 1 over x squared, x minus 2. As x gets very, very large, well, x squared times x minus 2 looks like an x cubed. So something growing as fast as x divided by something growing as fast as x cubed, it looks like something growing like 1 over x squared. So as x goes to infinity, 1 over x squared goes to 0. So I have that this is asymptotic to y equals 0, and that is my horizontal asymptote. You can also note that the degree of the numerator is less than the degree of the denominator. Therefore, the let's look at some asymptotic behavior. So the asymptotic behavior, let's say, as x goes to 0. So as x goes to 0, well, y? Well, as x goes to 0, this just goes to 1. As x goes to 0, x minus 2 approaches negative 2. So this is a negative 2. And this is just x squared. So as x goes to 0, let's see what happens as x approaches 2. So the asymptotic behavior.
Can you explain how you got that again?
Sure. As x approaches 2. So the trick is, if you come out with something that makes sense, you write it down. If it's going off to infinity, then you don't substitute in the value. And that's the trick for everything. So here, I'm approaching 0, x equaling 0. So I let x equal 0 here, so I get a 0 plus 1. I put in a 0 here, but then you're dividing by 0. That doesn't make sense. So you keep the x squared, because if you didn't, it wouldn't make sense. Here, if I plug in 0, I get 0 minus 2, which is a negative 2. So in the numerator, I have 1. In the denominator, negative 2, x squared. Is that clear? So basically, you plug in, and so long as it makes sense, you're happy. Okay, let's do the same here. Let's do the asymptotic behavior as x approaches 2. Well, as x approaches 2, x plus 1 approaches 3. 2 squared approaches 4. X minus 2, that goes to 0, but then that means you're dividing by 0, so keep it. So that's your asymptotic behavior. So what you notice is that if x is very close to, these like 2, then this x plus 1 will be close to 3. This will be very close to 4, but this whole quantity near x equaling 2 would be something like 1 over 0 or something. Well, 3/4 is 0, which means it's going off to infinity somehow, which is how you got your vertical asymptote. And so let's actually look at the actual behavior of it. So now let's try to sketch the graph of this. So now let's sketch the graph. And so let's see if I can do this as best I can. It's moving around a little bit, but okay, so let's put in, I guess I can just put in my tick marks. I don't have to be too small. So here are my tick marks. After I put in all my tick marks, let me just put in my vertical and horizontal asymptotes. And then note denote the x and y. Now, let's see, we have a x equals 0. I have x equal 2. I have y equals 0. So those were my asymptotes. I have a x-intercept at -1. So let me put that down. Okay, good. And now let's fill in everything else. So with the x and y intercepts, that's all you get. Now let's look at the asymptotic behavior. As 0, I have that it looks like a negative 1 over 2x squared. So the half doesn't really make that big of a difference, but it looks like a negative 1 over x squared. Well, 1 over x squared looks like this. So negative 1 over x squared looks something like this. So down here, I've got to be close to the axis down here. I have to approach this. So I know from here, I have to be near this, go through this, and then eventually be close to this. So let's draw this. The only way it looks could be something like this, and then down. Okay. Over here, it's got to look something like this. It cannot cross the x-axis. Okay. Next, at x, as x is close to 2, it looks like 3 over 3 over 4 x minus 2. So it looks something like 1 over x minus 2. So it's just a translation of 1 over x. So it should look like something like this over here and something like this over here. So on this side, it looks something like this. Oh, come on. Sorry, it's slipping. Okay, so it looks something like this. Not too bad. Okay. On this side, it's got looks something like has to approach the x-axis, this asymptote over here, and this asymptote over here. So it's got to look something like this over here. Don't really know how high that goes, but and that's the sketch of y equaling x plus 1 over x squared x minus 2. So that's what the sketch of the graph looks like, something to that effect. Now, I've certainly exaggerated some of these, how high it goes over this and then approaches it, but it has that general flavor and that general sort of curvature like that, and this sort of curvature. So this is what it basically looks like. If you actually sketched it on a computer, you wouldn't get all these aspects. It would look too flat. But these are the characteristics of this graph. These are the important characteristics of the graph. Okay, so let me do the next problem. Problem number 9. Determine the domain and range of the composite function f composed with g. So let's do that. So first, f composed with g at x will equal, well, wherever I see an x in the formula for f, I'm going to replace x by the formula given by g. So wherever I see an x here, in this formula, I'm going to replace x by 1 over x minus 2. So this will equal 1 over. Replace x by 1 over x minus 2. minus 1. And that is your function. Okay? So I could simplify this if I want, but since I'm finding, well, let me not simplify it to find the domain, but then let me simplify it maybe to find the range. Okay, so let's find the domain of F composed with G. So in general, remember you do not want to divide by 0. And so I do not want this is equal to 0 because I don't want to divide by 0. Also, I do not want that x minus 2 is equal to 0 because I don't want to divide by 0. And so maybe I'll put it as not equal so you can, even though usually when we find the domain I say equal, let me just write not equal so that you know that it's really, it's not equal. So 1 over x minus 2, adding 1 to both sides of my equation is not equal to 1. Cross multiplying, x minus 2 is not equal to 1. Adding 2 to both sides of my equation, I get that x is not equal to 3, nor is it equal to 2. And so the domain of my function, f composed with g, is the union of two open intervals from -infinity to +2, from 2 to 3, union 3 to infinity. So these 3 open intervals. And that is the domain of the composite function. Let's find the range of this composite function. F composed with G. And so let's simplify this first. So let's simplify. F composed with G. Simplifying a function may change its domain, but in general, it will not change the range. So I didn't simplify for the domain because in general, it's very problematic to simplify when you're finding the domain. In general, you're not going to usually change the range. It's very unlikely. Okay, so let's see. F composed with G. At x was equal to 1 over x minus 2 minus 1. So let me multiply and divide by x minus 2. So this is going to equal x minus 2 over, the x minus 2's cancel, 1 minus a -1. Let's multiply that inside the parentheses. So it's a negative x plus 2. So let me simplify this. So this is equal to x minus 2 over 3 minus x. Okay, good. So now let's figure out the range. The range of f composed with g. Well, if you look here, this is just, again, we could have done what we did in the previous problems, but notice that this is a rational function. And so to find the range of a rational function, you can just look at, and let's suppose that this is a rational function where it's a linear polynomial divided by another linear polynomial, then the range will just be the ratio of the leading order coefficients of the numerator and denominator. And so I have 1 divided by -1 is a -1. So therefore the range is everything except for -1. That turns out to be, oops, the vertical, well, the horizontal asymptote. So if you look at the horizontal asymptote for this function, the horizontal asymptote will be y equal -1. And it turns out that in this case, you don't happen to cross the horizontal asymptote, even though you could in general, but not for a linear function divided by another linear function, because it's just a translation of 1 over x. And 1 over x is a hyperbola, is a rotation of a hyperbola. And hyperbolas have the strange property that they never touch their asymptotes. And so because of that, we happen to know that this actually doesn't cross the horizontal asymptote. Okay, let me do problem number 10.
So the -1 comes from the horizontal asymptote.
Yeah, it's this is negative, the -1 is your horizontal asymptote. So if you actually drew the sketch of this graph, you have I guess, a hole in it and I think a hole. No, you don't. You may have a hole at the, yeah, you do. And you have you have hole it too. You have a hole and you have a horizontal asymptote. Okay. Let me do problem number 10. Show the following function is injective. Oh, okay. With the domain of f equaling 0 to 2. The closed intervals 0 to 2. Well, we have that x1 and x2 are in the closed interval 0, 2. Okay. And they're such that the function at x1 is equal to the function at x2. I then want to show that x1 is equal to x2. That will show that this function is injective. So 4 minus x squared is equal to 4 minus x2 squared radical. And so since the square is injective, I can square both sides of my equation. Since the square is injective for values greater than or equal to 0, then I can square both sides of my equation. So this roots. So I'm not getting rid of, so this is, since y equaling x squared, oh, come on. Since y equaling x squared is injective for x greater than 0. Well, greater than or equal to 0, let's say.
What does injective mean?
That f of x1 equaling f of x2 implies that x1 is equal to x2. Sometimes people call this one-to-one, but that's what injective means. Injective means that if f of x1 equals f of x2, then x1 is equal to x2. It satisfies the horizontal line test. So squaring both sides of my equation, I get that 4 minus x1 squared is equal to 4 minus x2 squared. Subtract 4 from both sides of your equation. Ooh, equals minus x2 squared. So I have that x2 squared minus x1 squared is equal to 0. So let's factor this. And so if I factor this, I get x2 minus x1 times x2 plus x1 equals 0. Since this is a difference of squares, and so this is just the product of the sum and difference of two terms. Set each factor equal to 0. By the 0 factor. So x2 minus x1 is 0. x2 plus x1, 0. Okay. Now, therefore, x1 is equal to x2, or x2 plus x1 is 0. Well, we're solving this on the interval 0 to 2. Then the only way that this can be a true statement is if x1 is equal to 0 and x2 is equal to 0. That's the only way you can add two non-negative numbers, two numbers on the interval 0 to 2 to get that their sum is 0. You must have that each of them are 0. But that implies that x1 equals x2. So no matter what, I have that x1 equals x2. But if x1 is equal to x2, then this says that f is injective on this interval. And that's what I wanted to show. Okay. So an injective function is either always increasing or decreasing or constant. So it never starts to increase, but then in other places it decreases or whatever. So it always satisfies this horizontal line test. Let me do problem number 11. Determine f inverse, the domain of f inverse, the range of f inverse for the following function. F of x is equal to radical x squared minus 1 with domain of f equaling negative infinity to negative 1. So let's do this. So first off, let me rewrite f of x and write it as y instead. So replace f of x by y. Now let me interchange x and y. So interchange x and y here. That is the definition, basically, of the inverse function. The inverse function is just reversing the roles of x and y, of your dependent and independent variables. Okay. So now I want to solve for y. Oh, and so notice here, maybe I should say that, the domain of my function here says that x here, and maybe I should have this in red, that x here is less than or equal to -1. When I interchange x and y, this is saying that y is less than or equal to -1. Square both sides of my equation. I can do that because x squared is injective on this region. Okay. And so I get that this is equal to x squared. The square gets rid of the square root, so that's y squared minus 1. So let's solve for y. Add 1 to both sides of your equation. So y squared is equal to x squared plus 1. Take the square root of both sides of my equation. So y is equal to plus or minus the square root of x squared plus 1. But the domain was restricted to this. So the y values here had to be negative, had to be less than or equal to -1. Therefore, this sign cannot be positive. It must be negative. And so let me write my inverse function. So I've determined my inverse function. My inverse function is just minus rad x squared plus 1. And that is the formula for inverse function. Let's find the domain of the inverse function. The domain of your inverse function, well, it's the same as the range of my original function. But the range of my original function, looking here, is just that y is less than or equal to -1. And so this is just y is less than or equal to -1. So it's the goes from -1, negative infinity to -1. Oh, wait 1 second. It's the range of the inverse function I wanted. The domain of this, I'm sorry. So it's the range of your original function. Well, your original function here is never going to be negative. And your x values go from negative infinity to -1. And so my y values here go from 0 to positive infinity. And so this is just 0 to infinity. And that's the domain of my inverse function. Now let's find the range. the range of my inverse function is the same as the domain of my original function. Well, the domain of my original function is just that y is less than or equal to -1. And so the range is y being less than or equal to -1. So negative infinity to negative, the closed interval from negative infinity to -1. And that is the range of your inverse function. Let me do problem number 12. The cable of a suspension bridge is in the shape of a parabola given by the equation x squared minus 2500y plus 25,000 equaling 0. In the coordinate system shown in the illustration, so this coordinate system, with the distance in feet, how far above the roadway, so this is my roadway, is the cable's lowest point. So what is this cable's lowest point? Okay, and each of these are 500 apart. Okay, so let's do that. So I have that x squared minus 2500y plus 25,000 is 0. Therefore, 2500y is equal to x squared plus 25,000. Let's divide both sides of my equation by 2500. And so y is equal to x squared over 2500 is 10. So this just looks like a parabola. And so this is quadratic.
Excuse me?
Yes.
Where did you get 10 from?
Oh, what's 25,000 divided by 2500?
Oh, okay.
Well, everything cancels, except for one of the tens. So 250 divided by 25 is 10.
Okay, thank you.
Sure. No problem. Okay, so that's good. So this is a parabola. This is quadratic in x. And so this is a parabola. So let's look here at A. A in this case is 1 over 2500, which is greater than 0. So therefore, this parabola is going upward. So it's upward. So it opens upward. Yeah, actually, maybe I should say opens upward. So this means that that it has a minimum value, and the minimum value occurs at the vertex. And so that this has a minimum at the vertex. Which is good because we wanted to get the lowest point. And so what I have to do is look at the coordinates of the vertex. Well, first, let's, just like what we did before, let's find the axis of symmetry, because that has a nice formula. That's the only reason that we're going to actually do it, is because it has a formula, x equal negative b over 2. But okay, so I have that x is equal to a negative, b is 0, a is 1 over 2,500. But whatever, that's 0. So you have 0 divided by anything is 0. Any non-zero number is 0. So I have x equals 0. So now let's determine the y value. So let's determine the vertex. I can determine the y value of the vertex by just plugging in for x 0. Okay. And so let's add another page here. So I have 0 plus 10 is 10. Good. So that means that the lowest point, the minimum is 10. So the lowest point for this bridge, for these cables, is 10 feet above the roadway. And so the cables dangle down up to 10 feet above the roadway. Let me do problem number 13. In 20 years, a father wants to accumulate $40,000 to pay for his daughter's college expenses. If he can get 6% interest compounded quarterly, how much must he invest now to achieve his goal? Okay, so let's write the formula for compounded interest, which is really the same as the exponential growth equation. It's just with different notation. So, but I'll write the compound. So the compound interest formula says that A equals P 1 plus R over N to the power NT. Okay. So let's figure that out. And we're doing this quarterly. So A is equal to, well, maybe I'll plug in everything. So A is the amount that he wants, and he wants $40,000. We don't know how much he has to invest now. That's what we're trying to determine. Well, this is 1 plus. The interest rate is 6% per annum, so 0.06. There are 4 quarters in a year, so there are 4 compound periods in a year if we are compounding quarterly. And we're going to do this for 20 years. So let's do this. So I have 40,000 is equal to P. 0.06 divided by 4 is 0.015. So this is 1.015 to the power 4 times 2080. And so the principal should be 40,000 divided by, actually, let me write it this way. Let me write it with a negative exponent. It may look nicer. So P is going to equal $40,000 divided by 1.015 to the 80, which is the same as multiplying by its reciprocal, changing the exponent from positive to negative, 1.015 to the negative 80. So that's how much you need to invest. Now, with money, we actually want an approximation to this. So since, there's a word problem and it's dealing with money, let's to the nearest penny. So this is going to be approximately 12,155.6059. And so this is approximately $12,155.61. So that is the amount that you should invest so that you have $40,000. Let me do problem number 14. The biological half-life theophylline is 4.5 hours for smokers. Find the amount of the drug retained in a smoker's system after 12 hours after a dose of 1 unit is taken. Okay, so let's do that. So the half-life is 4.5 hours. We originally take 1 unit. We want to determine how much remains after 12 hours. Okay. So I can use a formula. So I have A is equal to the original amount, A sub 0, e to the minus lambda t. So that's the formula for exponential decay. I know a formula for half-life, but I'll assume I don't remember the formula for half-life and just determine lambda from there. So I know that actually lambda is equal to ln2 over the half-life, but I'm going to derive that instead of just sort of using that formula. Okay, so we start out with 1 unit. The half-life is 4.5 hours. And well, after 4.5 hours, you have half of what you started with, 1/2. So let's take ln to both sides of my equation. Ln e to any exponent will just be that exponent. And so I get, and ln of 1/2 is just minus ln of 2 by the properties of logarithm. Ln e to any exponent is the exponent. So let's divide both sides of my equation by negative 4.5. So lambda is equal to ln2 over 4.5. What I just said previously, that the lambda, the decay constant, was just ln2 over the half-life, which in this case was 4.5. And so I have the following. I want to determine the amount after you start out with 1 unit. You have the decay constant of ln2 over 4.5. And we do this for 12 hours. Okay. And so the amount A is equal to the minus. 12 divided by 4.5 is just 8/3. So this is e to the 8.5, 8/3 ln of 2. Okay. And so this is the same as e to the ln 2 to the power negative 8/3. E to ln of anything is just that exponent. And so the amount is equal to 2 to the negative 8/3, which is just 1/2 to the 8/3. Okay. Well, maybe I'll write it as, yeah, that's right, as 1/2 to the 8/3. Okay. Which is 2 2/3. And so this is going to be 1 over 2 squared is 4 times the cube root of 2 squared, which is 4. Okay. And so that's the amount. Let me plug that into my calculator to get an approximate amount. For these word problems, usually we like approximate amounts. And so let's plug that in. So the amount is approximately, so 4 times 4 is 0.157490131. So that's the approximate amount, about 1/6 of a unit is still there after 12 hours. Let me do problem number 15. The population of the Earth is approximately 6 billion people and is growing at an annual rate of 1.7%, 1.9%, sorry. Assume, so 1.9%. Assuming a Malthusian growth model, find the world's population in 30 years. So I'm assuming that this grows exponentially. A equals A0e to the kt. I want to figure out the amount of, I want to figure out the world's population in 30 years. Well, we start out billion. I'm going to write everything in billions. A population is 6 billion with a growth constant of 1.9%. And I want to do this for 30 years. And so A is equal to 6, E to the 0.57. Again, let's try to find an approximation for this. And so the amount is in 30 years, 10,609,602,309, and that's all my display shows. So that's the approximate population of the Earth in 30 years from when this was written. Problem 16. Solve the following for x. Log base x of 9/4 is equal to -2. Let's rewrite this logarithmic equation in exponential form. And so the base is x, the exponent, and the result is 9/4. Cross multiply. So if I cross multiply, I get 9x squared equals 4. Okay, so let me take the square root of both sides. So by the square root property, I have that 3x is equal to plus or minus 2. And so I have that x is equal to plus or minus 2/3. Now, since this is a base, I have to have that the base is greater than 0 and not equal to 0 nor 1. And those are stipulations so that, well, we had an injective function. And okay, so I can't have a negative. So this has got to be positive. And so my answer is a positive 2/3.
Can you explain how you got 9x squared equals 4?
Cross multiply. 1 over x squared equals 9/4. So you cross multiply. 9 times x squared is 9x squared. 4 times 1 is 4. Okay? So it's just cross multiplication. Or you can think of you're multiplying both sides of your equation by 4x squared. That's an equivalent statement. But actually, I just said that we're cross multiplying. Any questions about that? Good. Okay. Let me do problem number 17. Sketch the graph of the following function. F of x equals -3 plus log base 3x plus 4. So first off, let's write f of x as y. So y equals -3 plus log base 3 of x plus 4. Let me subtract, add 3 to both sides of my equation. So y plus 3 is equal to log base 3 of x plus 4. So this is just going to be a translation. And so I'm going to translate y equal log base 3 of x. And I'm going to be translating this, well, 4 in the negative x direction. So 4 to the left. And I'm going to be, since I'm adding 3 to y, I'm going to be going 3 units in the negative y direction. So I'm going to be going down by 3 units. Okay. Notice that the base here is 3, which is greater than 1. So this just looks like the graph of log of x or ln of x. They all have the same general shape for any base greater than 1. So let's sketch the graph of this. As best I can. Oh, maybe I should, well, so x, y. So let's first off sketch the graph of, well, actually, let's put some tick marks. Those are not very evenly spaced. Doing the best I can, which is not, still not a very good job. Okay, so let's sketch the graph of y equal log base 3 of x. Should look something like, oh, this is horrible. That's just too horrible. Again, everything is slipping when I try to draw. Not too horrible bad, not too great, but this is the graph of y equaling log base 3 of x. Okay, log base 3 of x. Okay. And so now I'm going to translate this by 4 to the left and down by 3. So let's translate 4. 1, 2, 3, 4. Actually, let me draw as a help, as a crutch. So I'm just going to use this as a crutch. So I'm just going to translate over the y-axis by 4 and down 3 for the x-axis. Which actually in this case just sort of means that this is going to be a vertical asymptote. Okay, so now let's sketch the graph. And so all I'm doing is I'm just translating this guy over. And so if I do that, oh, it's going to intersect here. Okay. Actually, let me copy this. Okay. Now let's bring this over somewhere. Let's paste this. Okay, as best I can. Let's get rid of these guys. Okay, so now let's move this guy over. If I can, let's move this guy over. Oh, I hope you're going to be able to move. Of course it doesn't move. Okay, so I hate you. Okay, so let's not. Okay, let's undo the move. Okay, so it just looks, it's gonna look something like, oh, actually that doesn't look so horrible. Okay, so it looks something like this. And I'll get rid of all this other extraneous stuff that came along with it. Oops, that was not extraneous. That was part of this guy, but this was extraneous. Okay, good. And this was something extraneous if I can get rid of it. So this, of course, I didn't want it to be red. I want it to be black. So this is the graph of my function. Just looks like this. Actually, I can just make it a little bit. I'll just make it slightly thicker. So this, voila, is the sketch of y equaling, and let's put it over here somewhere, y equaling -3 plus log base 3 of x plus 4. So that's what that looks like. Okay, let's do problem number 18. Find the decibel gain of an amplifier whose output voltage is 2.8 volts and whose input voltage is 0.05 volts. So your decibel gain of an amplifier, so decibel gain of an amplifier is just 20 log ratio output voltage over input voltage. And so your decibel gain is 20 log of 2.8 divided by 0.05. Well, let's do 0.05. And so your gain is 20 log of 56. And that's your answer. Volts. Decibels. Decibel. This is decibels. So that's your decibel gain, which is approximately, plug into your calculator, 35 decibels. So 34.96376054 decibels. Okay. Let's do earthquake. An earthquake has an amplitude of 8,000 micrometers and a period of 0.008 seconds. Find the measure on the Richter scale. So how large is the earthquake? And so the earthquake measures on the Richter scale log of A over P, the amplitude over the period. And the size of the earthquake on the Richter scale is log of your amplitude, which is 8,000 micrometers, and 0.008 seconds. So let's see how many microseconds that is. And so this is 0.008 seconds. So 8,000 divided by 0.008 is log of 1 followed by 1 billion, 1 million. So this is log of 1,000,000. And so this is just 6. There are 6 zeros, 2, 4, 6 zeros. So this has a magnitude 6 earthquake. So this is a magnitude 6 earthquake on the Richter scale. Let me do problem number 20. If K equals 0.116, how long will it take a battery to reach 90% charge? Assume that the battery was fully charged when it began charging. And so I have that K is 0.116. I have that the charge is 90% of the maximum charge. Let's call them charge M. Then let's figure out how long. It will take to get fully charged. Well, the charge, I'm sorry, 90% charge. The charge is just equal to the maximum charge times 1 minus e to the negative kt. Okay, so let me get another page here. Okay. Let's wait for the, okay, so it's still doing that. Okay, thank you. Get another page. So the charge is 90% of the maximal charge. Maximal charge I call M. 1 minus E to the minus K, which is 0.116 T. The M's cancel. Let's subtract 1 from both sides of my equation. And so I get a negative 0.1 is equal to, let's get some more room, negative 0.1 is equal to a negative e to the negative 0.116 t. Let's cancel out the negatives and then take log of both sides of my equation. And so I have ln 0.1 equals ln e to the exponent negative 0.6 t. Ln e to the exponent is just the exponent, negative 0.116 t is equal to ln 0.1. Let me negate both sides. So 0.116 t is equal to ln of the reciprocal of 0.1, which is 10, by 0.116. Okay. And so I have that the time is ln 10 over 0.0116. Let me get a new page here. I get ln of 10 divided by 0.116 is approximately 19.84987149. And that was in hours. So this is in hours. Wouldn't make sense for it not to be. And so there are 60 minutes in an hour. So the fractional part by 60. And so you get 50 minutes and 9922. So this is hours, minutes. 22. 19 hours? That's got to be minutes. 228. Okay, 8. 8948. And so it's 19 hours, 50 minutes, and let's multiply by 60. 59.5373687.8 seconds. Okay. So let me do problem number 21. A mole of gas expands, so it doesn't change temperature, to triple its volume if the gas temperature is 400 degrees is absorbed. And so I have here that the temperature is 400 degrees Kelvin. Okay. I know that the final volume is triple the initial volume. It says that it triples in volume. I know that so I want to figure out the energy. And I know that Reynolds number, R, is 8.314 approximately. And so I know that the ratio of the volumes, the final and initial volume, is just E to the E over RT. Okay, so I have that the final volume is 3 times the initial volume. So let's plug that in. Is equal to E to the energy, don't know what that is. R, which is approximately 8.314, and the temperature is 400. Okay. And so the initial volumes cancel. Of course, I'm assuming the initial volume is not 0. And so I have that 3 is equal to E to the E over let's multiply 8.314 times 400. So 3325.6. Take ln to both sides of my equation. So I have that ln 3 is equal to ln et, and the exponent is just the exponent. So this is just E over 3325.6. So let me multiply both sides of my equation by 3,325.6. So the energy is equal to 3325.6 ln 3. Let me approximate this. And so this is 3653.545027. Oh, and I should say that this is in joules. Okay, so that's the approximate energy. 22.
I have a
A
question.
word process. Yes, question.
On the exam, will you expect us to know all these formulas like off the top of our head, or are you gonna like for each problem are you gonna put the formula?
You should know these formulas. So
All of
there
them?
are just a few formulas that I gave in class. There weren't that many. Okay.
This one I haven't seen before.
Well, but that's in your book. So that's in your book. So so it's in your book on that particular chapter. So you would just look it up. I mean, if you don't know it, you just look it up. Okay. For this next exam, I think you have 2 days to do it. So you have 2 days. You should be able to look up a formula in a book in 2 days. Okay.
Oh, for the exam, you only gave us 1 day. Are you gonna extend it to 2?
It's Thursday. So Thursday, Fridays, actually it's 3 days. It opens on Thursday. You have all of it opens on Thursday and is due on Saturday. Right? So it's over 2 days. It's not quite 3 days, but yeah. So you have you have some time to look over it.
Oh, so you're gonna open it this Thursday then?
Yeah, it's whatever it says on the if you open it up, it'll well actually, yeah. If I guess you guys can see it, right? If you look under assignments, it tells you that the day it opens and when it closes. Okay, I think it's, I don't know. I have to look it up. It's sometime on Thursday, and and then it closes sometime on Saturday. I think, I don't remember. You'll have to look it up. I don't know the exact time off the top of my head.
Okay.
Okay, so let me do problem number 22. A word processor worth $470 when new had a life expectancy of 12 years. If it is now worth $189, how old is it? Okay, so let's figure out that. So, in allegation, they had the book. So its value is $189. The cost was $470. the number of years that expected, the life expectancy of this equipment is 12 years. And I want to figure out how old it is. Okay, so I have that the value V is the original value, its cost, C, times 1 minus 2 over expectancy times, well, the number of years, N. So that's its value after N years. Okay, let's give me another page. So I have the value is 189. The original cost is 470. I have that N is 12, and I want to determine little n. Okay, so 1 minus 1/6 is 5/6. Divide both sides of my equation by 470. So 5 over 6 n is 189 over 407. Take ln of both sides of my equation. And so n, ln of 5/6, bringing down the exponent out in front of the logarithm, with the ln of 189 over 470. And so n is equal to, let's divide both sides of my equation by ln of 5/6. So this is ln of 189 minus ln of 470 over ln of 5 minus ln 6. And that's your answer. And so n is approximately 4.996587873 years. So that's how old it is currently. Let me do problem 23. Find the pH of a solution with a hydrogen ion concentration of 1.7 times 10 to the negative 5 gram ions per liter. And so you have a concentration of 1.7 times 10 to the negative 5 gram ions per liter. Grams of ions per liter. Okay, so the pH is defined as the negative of the logarithm of the concentration of these hydronium ions. And so P, your pH is negative log 1.7 times 10 to the negative 5 And so, well, it is, this would be the same as the log of, negative log of 1.7 minus the log of 10 to the negative 5. And so that just becomes a negative 5. So this is just 5 minus log 1.7. And that's your pH. And so your pH is approximately 4.76955 1079. So that's your pH. 24. Same problem we did before. Losses in a long telephone line reduces a 12-watt input so this is 12 watts to an output of 3 watts. Find the decibel gain. So your decibel gain is 20 log ratio of your output over your input. And so, oops, this is equal to, okay, let's stop that. 20 is equal to 20 log of 3 over 12, 1/4. And so the decibel gain is 20 log of 1/4, so that's a minus log of 4. And so this is approximately, plugging into my calculator, negative 12.0411983 decibels. And so you're losing about 12 decibels. Since you went, your input was 3 watts, 12 watts, and your output was 3 watts. 25. So I want to solve this. So this is just 3x times 3 cubed plus 3x equals 84. 3 cubed is 27. 27 apples plus 1 apple is 28 apples. 20. Okay. So this is equal to 28 times 3 to the x. Divide both sides of your equation by 28. And so 3 to the x equals 3. Since the exponential function is injective, and the two outputs are the same, then I must have that the exponents are equal. So x is equal to 1. And that's your answer. 26. Solve for x. ln 3x minus 5 equals 7. Let's change the logarithmic form. So the base is e, the exponent is 7, and the result is 3x minus 5. Add 5 to both sides of your equation. Divide both sides of your equation by 3. And so x is equal to 1/3 times 5 plus e to the 7. And that is your answer. Note that if you plug x into the original equation, the 3's cancel. And so you just get 5 plus e to the 7 minus 5. The 5's cancel. So you get ln of e to the 7, which is a positive number. Therefore, this is defined. And so that is the solution to that equation. It's not extraneous. 27. Solve for x. Log x plus log x plus 21 equals 2. So by the properties of logarithms, I have that the log of, let's multiply x times x plus 2. So it's x squared plus 2x is equal to 2. So now, ooh, that's a 21 plus 21x. Let's rewrite this logarithmic equation in exponential form. And so I have that that the base is 10, the exponent is 2, and the result is x squared plus 21x. Subtract 100 from both sides of my equation. So x squared plus 21x minus 100 is 0. That's factor. X plus 25 times x minus 4 is 0. This is a monoquadratic trinomial. Plus times minus is minus. I want two whole numbers whose product is 100 and whose difference is 21. So 25 and 4. Put the larger factor first. So since so by the zero factor property, I have that either x plus 25 is 0 or x minus 4 is 0. Subtract 25 from both sides of your equation. So x is equal to negative 25. Add 4 to both sides of your equation. So x is equal to 4. If I plug in negative 25 into this first equation here, I get the log of negative 25. Well, that doesn't make any sense. So I've got to get rid of that. That's an extraneous solution. If x is equal to 4, well, log of 4, I can calculate that. 4 plus 21 is 25. I can calculate the log. So therefore, x equaling 4 is a solution to my equation. Let me do problem number 28. Only 25% of the carbon-14 in a wooden bowl remains. And so only 25% of the original carbon-14 remains. How old is the wood? So I want to figure out T. I know that the half-life of carbon-14 is approximately 5,700 years. Okay. And from there, I know that the decay constant is just ln of 2 over the half-life, 5,700. The equation for determining how much remains if you have radioactive decay is just A equaling A0 e to the minus lambda t. And so I have that 25% of the original remains The half-life was 5,700. So lambda is ln 2 over 5,700 times, well, t. I can cancel the a sub zeros, assuming that the original amount is not 0, which is always the assumption. You can solve this. Let's take ln of both sides of my equation. It's 0.25 is equal to ln of e to any exponent, which is just the exponent, negative ln 2 over 5,700 t. Let's negate both sides of my equation. And so if I do that, this just becomes ln of 4 equals t ln 2 over 5,700. So let's divide both sides. Really? So
How did you get 4?
Pardon?
How did you get 4 from 1?
Oh, how did I get 4? Here, let's wait 1 second. Okay, let's see if I can do this. Okay, 1 second. So this is ln of 0.25 is 1/4. Okay. And maybe I'll put the t here. Okay, so remember, and so this is ln of 4 to the negative 1. Negative t ln 2 over 5,700. Okay. So now I can just put the negative out in front. I can always exponent out in front of a logarithm. That's one of the properties of logarithms. And so this is equal to negative ln 4, which is equal to a negative t ln 2 over 5,700. Okay. Negatives cancel. Let's, and so this is equal to ln of 4, which is 2 squared, equals t ln 2 over 5,700. You can all just do these on your calculator, but which is equal to I can bring the 2 out in front, so that's a 2 ln 2 is equal to ln t ln 2 over 5,700. The ln 2's cancel. And so let's just multiply both sides of my equation by 5,700. 5,700, oops. 5,700 times 2 is 11,400. And so I get that this object was 11,400 years old. Any questions about that? Okay, so let me do
Yes.
Yes, question.
How did you get the half-life? How did you do
Oh, how did you get the half-life? You have to look it up.
that? Okay.
So the half-life, that is something that's given in the book, as approximately 5,700 years. Okay,
Okay.
so that's the half-life of carbon-14.
Is that always? So whenever we see half-life, it's always
Yep.
that approximate number?
Yep.
Okay.
Yeah. So for carbon-14, the agreed value is approximately 5,700 years. Okay. Which was determined by William Libby, at UCLA. Okay, so 29. Again, you can look up that value on the internet or just look it up in your book. Okay, problem number 29. If $1,300 is deposited in a savings account, so $1,300, paying 9% interest, compounded quarterly, so there are 4 quarters in 1 year. How long will it take the account to increase to $2,100? So that the amount A in your account. So the compound interest formula is just P1 plus R over N to the NT. So let's just plug everything in. And so the amount, 2,100, is equal to the principal, 1,300, times 1 plus the interest, which was 0.09, over, so I wrote 9% as a decimal, 0.09, over 4, because there's 4 quarters in a year. And I don't know how many years yet. Divide both sides of my equation by 1,300. So 21 divided by 1,300, I can cancel the zeros, equals 1. 0.09 divided by 4 is 0.0225 to the 4t. Take ln of both sides of my equation. So this is ln 21 over 13 equals, bring down the exponent out front, 4t, ln 1.0225. Divide both sides of your equation by 4 ln 1.0225. So t is equal to ln 21 over 13 divided by 4 ln 1.0225. And that is your answer, years. So let me get another page here. And so t is equal to approximately 5.388314,109 years. Let me do problem number 30. Solve the following equation in the field of rational numbers. 2x cubed minus x squared plus x minus 2 equals 0. So let's first use the rational root theorem. So the factors of 2 are 1 and 2. The factors of 2 are 1 and 2. Therefore, the possible rational roots. First divide p by 1. So plus or minus 1. And maybe I'll write as 1 over 1. Plus or minus 2 over 1. Now divide each of these by 2. And so plus or minus 1 over 2. 2 over 2 can be reduced, so we don't write that in our list. And so let's try to factor. Let's see if I get another page here. Okay, so let's try 1, because 1 works. Yeah, cancel, cancel. So this is 2 minus 1, 1 minus 2. Please note that if you look at the coefficients here, notice that the 2's cancel and the 1's cancel. Since all the coefficients cancel, what you try for a root is 1. If everything does cancel, 1 is a root. So if all the coefficients cancel, you know that 1 is a root. So let's try it. 2 times 1 is 2, minus 1 is 1. 2 minus times 1 is 2, minus 2 is 0. Voila. So you're done. Now, what I note here, and so 1 is a rational root. I can do this several ways. I have here that 2x squared plus x plus 2. I want to see if that has any rational roots, my reduced equation. I could just see, this is one of the few times that Descartes' rule of sign actually helps us. I could actually see that there are no positive roots nor negative roots to this. And so there are no real roots to this equation. And so I could just say, okay, well, therefore, there are no additional rational roots. Or I could just say, well, the discriminant d is equal to b squared minus 4ac. And so my discriminant is just b, which is 1 squared minus 4, a, which is 2, c, which is 2. So 1 minus 16 is a minus 15, which is less than 0. Since my discriminant is less than 0, that implies that this has no real roots. So there are no real roots. If there are no real roots, then there's certainly no rational roots. Therefore, the only rational root was x equal 1. And that is the solution to my equation. The only root in this case was 1. And that's it. Okay. Solve the following equation for x in the field of complex numbers. 2x cubed minus x squared plus x minus 2 equals 0. So first let's find the rational roots. So P is equal to plus or minus 1, plus or minus 2. Q is plus or minus 1, plus or minus 2. The possible rational roots, P over Q, plus or minus 1, plus or minus 2, plus or minus 1/2. 2 over 2, of course, is 1, so you don't have to look at that one. So let's try 1. So I have 2x cubed minus x squared plus x minus 2. Drop down to 2 times 1 is 2 minus 1 is 1 times 1 is 1 plus 1 is 2 times 1 is 2 minus 2 is 0. Okay, so now let's try to factor the reduced equation. Let's try to solve the reduced equation. Let's solve 2x squared plus x plus 2 equaling 0. And let's do that over the complex numbers. Well, let me use the quadratic formula. And so I have that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so x is equal to negative 1 plus or minus the square root of 1 minus, 4 times 2 times 2, 16 is a negative 15, all divided by 2 times 2, which is 4. And so I have that x is equal to negative 1/4. Well, actually, let me write it this way. X is equal to negative 1 plus or minus I rad 15 over 4. And so the roots of my equation are x is equal to 1, negative 1 plus or minus I over times rad 15 all over 4. And so those are the 3 roots, 3 complex roots to my cubic equation. Let me do problem number 32. I want to solve the following equation for x in Z3. Okay, so let's solve this. It's a cubic equation. So I know that the roots of this are going to be the same as find the roots of this. All I have to do is look for linear factors. And so since there are only 3 numbers I have to look at in Z3, I might as well just look at those and see which of those are factors. So first, let's look in Z3. My equation then becomes, well, 2x cubed. Let's add 3 to the negative 1. So that becomes plus 2x squared plus x. Let's add 3 to negative 2. So that becomes plus 1. And so I want to solve this equation. So let's see if any of these. So I try 0. Obviously 0 doesn't work. So let's try 1. See if 1 works. If 1 is a root of my polynomial. 2x cubed plus 2x squared plus 1x plus 1. Down to 2 times 1 is 2. 2 plus 2 is 4. So if you divide 4 by 3, you get a remainder of 1. Times 1 is 1. Plus 1 is 2. Times 1 is 2. Plus 1 is 3. But 3 is a factor of 0. And so 3 is a factor of 3. So the remainder is 0. And so that's just equal to 0. So let's try, I don't know, try 2. So let's drop down my 2. Times 2 is 4. But again, 4 mod 3 is 1. Plus 1 is 2. Times 2 is 4. But again, 4 mod 3 is 1. Plus 2 is 3, which has a remainder of 0. Okay, good. So those are solutions. Now I guess that, let's see, I don't know, that's just 1 plus x. So that's going to be a 2. So 2 times 2 is 4. So 4 mod 3 is 1. Plus 2 is 3. So 3 mod 3 is 0. So therefore, I have found that, I just need one more line here.
Professor, for me,
Question.
yeah,
Question.
Okay, can you hear me?
Yes, I can hear you.
Oh, okay, sorry. I had so much noise. I'm not understanding when you mean 4 mod 3. What does that mean?
4 mod, So again, remember,
Mm-hmm.
4, well, what is 4 mod 3?
Mm-hmm.
Or anything else? It means divide 4 divided by 3. Actually, let's do 5 mod 3. Let's do 5 mod 3. So
Okay.
I would divide 5 divided by 3 is 1 with remainder of 2.
Oh, I see what you're
The
doing.
mod
Okay.
is the remainder. All I'm looking at is the remainder. I don't care about the quotient, just the remainder. And so this would
Okay.
equal 2. And so that's how I got like -1 mod 3,
-1.
right? Okay, so that's just equal to 2, right? Because again, you can always add, remember, all you're doing is dividing by 3 and you're finding what your remainder is, right? And so if you do -1 divided by 3, well, that's just going to be -1 plus 2/3. So the remainder is 2. Okay. Or you can,
Uh-huh.
or you can think, and this is actually the way I sort of, my head, because it's easier than sort of dividing, is you can just say, well, I can always just add multiples of 3, and that won't change my value. Okay, so I can either add or subtract a multiple of 3. So -1, well, and I want to get a number equal to 0, 1, and 2. Well, what can you add the -1 at 3? And so -1 mod 3 is just 2.
Okay, so what we're trying to do is just get 3.
Well, it says in Z3. And so what we're doing here is in Z3 only has 3 numbers, 0, 1, and 2.
Mm-hmm.
Okay. And so what I'm doing here is I'm changing all these numbers, 0, 1, or 2, by either adding or subtracting a multiple of 3. So I added 3 here, added 3 here. Now they're all numbers of the form 0, 1, or 2. So now 2 plus 2 is 4, right?
Mm-hmm.
But
Yes.
again, I want to either add or subtract a multiple of 3 to get something that's either 0, 1, or 2. So that's how it becomes 1. So that's
Okay,
how
I
2
see.
plus 2 is 1. Okay?
Okay,
And then the 2
thank you.
plus, yeah, and the 2 plus 1 is 3. But again, 3, you can subtract 3 to go. That's how I'm doing all of these things in Z3. Now, of course, if it said Z5, you would do the same thing, but
By 5.
subtracting multiples of 5. Okay, then
Got it.
let's go on.
Thank you.
So good. If you don't understand anything, you ask me. So I
Thank you.
answer. Sure. Okay, so now let's solve it. So x is equal to, well, 1, 2, or 2. So those are the solutions to my equation, mod 3. So in Z3. Let's do problem number 33. Solve the following equation for x in the field of rational numbers. And so let's use the rational root theorem. And so let's find all the possible values, possible rational roots. Okay, that's kind of weird. So let's find all the possible rational roots. And so P is the factors of 4. Well, the factors of 4 are 1, 2, 4. The factors of 1, just 1. So the possible rational roots are divide everything by 1. So plus or minus 1, plus 2, plus or minus 4. Okay, so they're all nice numbers to look at. In this case, here, let's add another page. Let's try to, so these are all the possible rational roots. So let's try to factor this. So this is 1x cubed plus 1x squared minus 4x minus 4. Let's try -1. See if that works. So 1 minus 1 is 0, is 0. Minus 4 is -4, times -1 is 4, minus 4 is 0. Okay. And so let's try something else. Well, 2 should work. And so let's drop down 1 times 2 is 2, plus 0 is 2, times 2 is 4, minus 4 is 0. Okay, and lastly, let's try -2. And so let's drop down the 1 times -2 is -2, plus 2 is 0. Therefore, the roots of this equation are -1, 2, and -2. And those are the 3 rational roots of my equation. Let me do problem number 34. Following equation for x in the field of rational numbers. Okay, so again, it's the same sort of thing. So let's use the rational root theorem. So let's try to determine all the possible rational roots. So the factors of 1 are plus or minus 1. The factors to, oh, it's now moving. The factors of 2 are plus or minus 1 and plus or minus 2. So therefore, the possible rational roots, and maybe I'll just write that. So the possible rational roots are therefore P over Q plus or minus 1. Divide everything by 1, divide everything by 2, so plus or minus 1/2. Okay, so let's try to solve this cubic. And so I have 2x cubed minus 3x squared plus no x plus 1. And so let's try 1. Okay. So let's drop down. 2 times 1 is 2, minus 3 is negative 1, times 1 is negative 1, plus 0 is negative 1, times 1 is negative 1, plus 1 is 0. Okay. Let's try 1 again. The reason I'm trying 1 is I notice that if you numbers, you get 0. You add up all these numbers, you get 0. Drop down to 2 times 1 is 2, minus 1 is 1, times 1 is 1, minus 1 is 0. And lastly, let's try negative 1/2. Drop down to 2 times negative 1/2 is negative 1, plus 1 is 0. And so my my solutions are x is equal to 1, x is equal to 1, and x is equal to negative 1/2. So those are the 3 roots to my cubic equation. Let me do problem number 35. I want to solve this equation for x in the field of x to the 5 minus 3x to the 4 plus 28x to the 3 minus 76x to the second plus 75 minus 25 equals 0. And so let's first try to determine rational roots. So let's see if I can use the rational root theorem to determine some rational roots. If I can, then I'll be happy. So P, the factors of 25, 1, 5, 25. Okay. Well, I'm here. I might as well see if I can do that. Okay. So 25. The factors of 1, just 1. So the possible rational roots, well, there aren't that many. So that's good. P over Q. Divide everything by 1. Divide everything by 5. Divide the 5 by 1. Divide the 25 by 1. And so I have 6 possible rational roots. And so let's write this down. So I have 1x to the 5th, negative 3x to the 4th, 28x to the 3rd, minus 76, x squared, plus 75, minus 25. Okay. So 1 plus 75 is 76. So I cancel that 76. 25, so 28 minus 3 is 25, minus 25 gives you 0. So let's try 1. So one of the possible routes was 1. Let's try it. Drop down to 1 times 1 is 1. Minus 3 is negative 2. Times 1 is negative 2. Plus 28 is 26. Times 1 is 26. Minus 76 is a negative 50. Times 1 is negative 50. Plus 75 is 25. Times 1 is 25. Minus 25 is 0. Let me add up all these numbers. So I get 27 minus 2 is 25. Plus 25 is 50. Minus 50 is 0. Let's try 1. So drop down to 1 times 1 is 1. Minus 2 is negative 1 times 1 is negative 1. Plus 26 is 25. Times 1 is 25. Minus 50 is negative 25. Times 1 is negative 25. Plus 25 is 0. Okay. And again, if you add up all these, you get 0. So let's try. Drop down to 1. Times 1 is 1. Minus 1 is 0. Times 1 is 0. Plus 25 is 25. Times 1 is 25. Minus 25 is 0. And so I come out with x squared. Reduced equation is x squared plus 0x plus 25 equals 0. So let's try to solve this reduced equation. Well, subtract 25 from both sides of your equation. Take the square root of both sides of your equation. Therefore, and let me just check those were complex. Yes, I'm doing this over the field of complex numbers. Therefore, the solution to this is 1, 1, 1, plus or minus 5i. So those are the 5 complex solutions to my equation. You don't really have to repeat, even though I'm repeating roots. You don't really have to do that. Let me do problem number 36. Solve the following equation for x in the field of complex numbers. X to the negative 5 times minus 8 x to the negative 4 plus 25 x to the negative 3 minus 38 x to the negative 2 plus 20 x to the negative 1 minus 8 equals 0. Multiply by x to the 5th. So you get by negative x to the 5th. Negative x to the 5th. And so you get, then let's rewrite the order. So I get 8 x to the 5 minus 28 x to the 4 plus 38 x to the 3 minus 25 x to the 2 plus 8 x minus 1 equals 0. Okay. So let us try to solve this. And first, I guess, let's try to see if I can find some rational roots to this equation. And so let's use a rational root theorem. So let's factor 1, factor 8, 1, 2, 4, and 8. Let's find all the possible rational roots. So divide by 1, divide by 2, divide by 4, divide by 8. Okay, so let's do that. And so I have here 8 x to the 5 minus 28 x to the 4, 38 x cubed minus 25 plus 8, there it is, plus 8 minus 1. Oh, wait. So that's 50. Wait. That's 16, 15. 2, 3. That's 51. That's, okay, wait 1 second. 28. Okay, so let's see.
I added them up and they do equal 0.
They do equal 0. Okay.
Yeah.
So thank you. I'm somehow not getting 0. That's 20. That's 46, 50, 46, 54, and I got 51. Okay, so let me just see if I wrote something wrong. Let me just, oh, it's because I wrote something wrong here. So this is, so that's, wait, 8 minus 28 plus 38 minus 25 plus 8 minus 1. Okay, so, well, let's see if it works. For some reason, in my head, I'm not getting that it works, but I'm probably doing something wrong in my head. Okay, so. Let's try 1. Okay, so 8 times 1 is 8, minus 28 is minus 20, times 1 is minus 20. So I get 18, times 1 is 18, minus 7. It works. Times 1 is minus 7, plus 8 is 1, times 1 is 0. Okay, so that worked. Let's see if this works. 26, no, 26 minus 26. Okay, that works also. So 1 works again. Okay, so that one works. So drop down the 8, times 1 is 8, minus 20 is minus 12, times 1 is minus 12, plus 18 is 6, times 1 is 6, minus 7 is negative 1, times 1 is negative 1, plus 1 is 0. Okay, but that one doesn't work. It almost works. Okay, so they're all fractions. So the 1 doesn't work, neither does the -1. So let's try a half. You have a half, a fourth, and an eighth. My guess here is that the half is easier. If it's going to work, a half should work rather than the other ones. But don't know. That's just a guess. Drop down the 8. Divided by 2 is 4. Minus 12 is a -8. Divided by 2 is 4. Uh-oh. -4. Plus 6 is 2. Divided by 2 is 1. Minus 1 is 0. Okay, good. I can actually divide this by 2 to make it easier. Not that it really matters in this case, but let's divide everything here by 2. So this just becomes 4. Oops. This just becomes 4, -4, 1. A half, I think, works. Let's try a half. So drop down the 4, divided by 2 is minus 4 is -2. Divided by 2 is -1, so you get 0. And again, you could divide everything by 2. But here, actually, it's pretty easy to see what the solution is. So this is going to be a 2 and a -1. So you should try half again. Let's try 1/2 again. And so I get 2 divided by 2 is 1. Okay. So I've solved this. They're just rational roots in this case. A lot of these are just rational roots. And so I get x is equal to 1, 1, 1/2, 1/2, and 1/2. And that is your solution. Question?
Yeah, I keep getting stuck on how did you get -28 to the x to the 4th?
Oh, how did I get this one? Yes.
Yeah.
So I'm multiplying by -x to the 5th. So I'm writing it actually in this opposite order. So the negative makes that a positive, x to the 5th. And then this positive becomes negative. And then I have a 28, x to the 5 times x to the -1. So you just subtract x, you just add the exponents. 5 minus 1 is 4.
Okay, so it's a proper, oh, sorry.
So I'm just multiplying through, but I like to write in descending order. So that's why I switched the order around.
Okay. Got it. Thank you.
Okay. Okay, so now let's do, that's problem 37. Oh, and it's got a little picture here. Okay, so problem 37. The open tray shown in the illustration is to be manufactured from a 12-inch by 14-inch rectangular sheet of metal by cutting squares from each corner and folding up the sides. If the volume of the tray is to be 160 cubic inches and x is to be an integer, what side squares should be cut from each corner? Oh, okay, so we want to just find integer solutions to this. So I have here that I have a 14 cutting corners from each of the 4 corners of size x by x, and then folding up each of these sides to make something look like this. So it looks something like this. Okay. And so the length of this end is just 14 minus 2x inches. Since I subtracted x from each side, the length of this side here is just 12 minus 2x inches. So 12 minus 2x inches. And this height here, well, it's just going to be this x because you fold it up, and this length here becomes its height. So this is x inches. I know that the volume is length times width times height. And so let's find an equation. I have that the volume is 160 cubic inches. And, well, the length is 14 minus 2x. The width is 12 minus 2x. And the height is x. Let me simplify this a little bit. So let's factor out 2 from this one, and it's a 2 from this first, and a 2 from the second one. And so this is just 4x times 7 minus x times 6 minus x. Divide both sides of my equation by 4. And so I get that 40 is equal to x, 7 minus x, 6 minus x. Let's multiply this out. So this is just 40 is equal to x. 42 minus 13x plus x squared. And so let's rewrite this. Multiply the x inside the parentheses. So we get x cubed minus 13x squared plus 42x. Subtract 40 from both sides is equal to 0. And I want to solve this over the field of rational numbers. Okay, so I want to be able to solve this on the rational field. Okay, so let's use the rational root theorem again to solve this. If you notice that the first step is always just the rational root theorem, as long as you're doing it over rational numbers or real numbers or complex numbers. So something that where it's either the rational numbers, that would be the first step. Okay, so let's find factors of 40. 1, 2, 4, 5, 8, 10, 20, 40. Q. Okay, so let's do Q. And so the possible factor, the factors of 1 is just 1. And so now let's find the possible rational roots. Let me get another page here. Okay, so let's figure out P over Q. So divide everything, all the P's, by 1. So you get 1, 2, 4, 5. It's factors of 40. 8, 10, 20, and lastly 40. So those are the possible rational roots.
Professor, I can't hear you no more.
Can you hear me now?
Yes.
Oh, okay, good. Sorry about that. I stepped on my mic. Okay, I sat on my mic actually. Okay, there's an on and off switch, and I sat on it. Okay, thank you. Okay, so let me get rid of that. Okay, so the first thing I checked was 2. I just sort of guessed, and 2 worked. So now let's try to solve this reduced equation. But I want to solve this on the field of rational numbers. So I can solve this. I could try to factor it, but I'd be like, I want 2 whole numbers whose product is 20 and whose sum is 11, and nothing works. So let's look at my discriminant. Let's see if I can even factor this for integers. And so d is equal to b squared minus 4ac and so 121 minus 80 is 31, 41, which is not a perfect square. Since it's not a perfect square, I know that this means that there are no rational roots. Okay, good. And so that means that the only solution, only rational solution to this was x equaling 2. And so we wanted to determine so the square is just going to be a 2 by 2 square. So we'll cut out a 2 by 2 inch square. So a 2 inch by 2 inch square. So that's what should be cut out of that. Okay, let me do problem number 38. Solve the following equation for x in the field of complex numbers. Okay, so 3x to the 5 minus 6x cubed minus 12x squared minus 192x plus 64. Okay, so first let's try to find the rational roots. And so let's do the rational roots theorem. And so the factors of 64 are 1, 2, 4. Okay, 1, 2, 4, 8, 16. Oh, I forgot the 2. 16, 32, and 64. Okay, so those are the factors of 64. Let's find the factors of 3. Well, the only factors of 3 are 1 and 3. So let's find the possible rational roots. P over Q. Divide everything by 1. So 1, 2, 4, 8, 16, 32, 64. Divide everything by 3, 1/3, 2/3, 4/3, 8/3, 16/3, 32/3, 64/3. Okay. 2, 4, 6, 7. That's going to be 14. 1, 2, 3, 4, 5, 6, 7, 8, 34. Okay, good. I have them all. So now let's try to solve this. Okay, so I have 3 x to the 5th minus 4 minus x to the 4th plus 36x cubed minus 12x squared minus 192 plus 64. 5, 4, 3, 2, 1, 0. Okay. If you add them up, you don't get 0. If you change the sign of every other row. Okay, so plus or minus 1 doesn't work. So you can either start using fractions, and I don't want to start using fractions yet. Ooh, a third might work. Actually, a third seems to work, at least part of the way through it. But let's try like +2. Let's try that first, even though in my head, 1/3 seemed to have worked pretty nicely. Okay, so drop down to 3 times 2, 6. Minus 1, 5 times 2, 10. Ooh, plus 36 is 46 times 2. That doesn't look good. Let's try -2. Let's try -2. This seems to be going off. See, 1/3 worked better in my head. Let's try 1/3. Let's try 1/3, because in my head, 1/3 worked better. Okay, so drop down to 3. Divided by 3 is 1. Minus 1 is 0. Times a third is 0. Plus 36 is 36. Divided by 3 is 12. That's why it worked so well in my head. Minus 12 is 0. Times 1/3 is 0. Minus 192 is negative 192. Divided by 3 is 64. Minus 64 is 0. Good. So the 1/3 worked. Okay, so now divide everything by 3. Okay. And so if I do that, I get 1, 0, 12, 0, negative 64. Let's try 2, because then 2 isn't too horribly bad to do. So let's try 2 or -2. See if one of those worked. 1 times 2 is 2, plus 0 is 2, times 2 is 4. Plus 12 is 16, good. Plus 0 times 2 is 32. Plus 0 is 32. Times 2 is 64. Plus 64, 64 minus 64 is 0. Try a negative. Let's say -2, because that will give me 0. Notice it's going to give me every other number will be 0. So drop down the 1 times -2 is -2, plus 2 is 0, times -2 is 0, plus 16 is 16, times -2 is -32, plus 32 is 0. Okay, good. So my reduced equation will just be x squared plus 16 equals 0. So I want to solve the reduced equation, x squared plus 16 equals 0. Okay. And I'm solving this over the field, I already forgot, of complex numbers. So that's good. And so subtract 16 from both sides of your equation. So x is equal to -4 plus or minus 4i. And so there's no way I could have fit it anyway. So I was trying to do this without having a new page, but that's going to be impossible. So let's try to solve x squared plus 16 equals 0. Subtract 16 from both sides. take the square, so by the square root property, x is equal to plus or minus the square root of negative 16, which is 4i. Therefore, my solution is x is equal to 1/3 -2 I did +2 -2 and plus or minus 4i. So that is the solution. That's a 5th degree polynomial to my 5th degree polynomial. Let me do problem number 39. Ooh, approximate. So I want to approximate the positive root of the following equation to the nearest 10,000th. Since I want to do this to the nearest 10,000ths, the bisection method is much too slow to be able to do that. And so I don't want to use the bisection method. So I want to use Newton's method because that will be faster. And so just so that it doesn't take me forever, I'll use Newton's method. So let's find the derivation. So first, let f of x equal x cubed minus x squared minus 2. Let's find the derivation. And so the derivation is just 3x squared minus 2x. And so I have that Newton's method is the following. You just pick x sub 0. So you'll just choose it arbitrarily. In this case, choose it as being some positive number. Hopefully not too far from your solution. Doesn't really matter what it is, but you know. Next, I use the fact that x sub n plus 1 is just equal to x sub n minus f evaluated x sub n over f prime at x sub n. Oh, the only stipulation on x sub 0 is that the derivation at x0 is not 0. So we don't want to be dividing by 0. Okay, so let's do this. So let's pick, if you do this at 1, it's positive, and at 2, it's still, I would say, I'm doing this. So at 1, it's negative, and at 2, it's positive. So let's pick x0 to be 1.5. And let's, actually, let me start up my calculator for a second. And let's plug in some numbers here. So this will actually help me to figure out what this is. The reason I picked a positive number to start at is that they said that they wanted the positive root. And so I started with some positive number. And it looked like 1.5 should be pretty close to a root. You know, somewhere between 1, it's a little bit bigger than 1, I think. Okay, so let's go, oops. Get rid of that. Why is that? Seems to always be on. Okay, good. So let's go here. Okay, so let's clear that. So I have x minus, so my formula is x sub n minus f, I'll put a little parentheses here, which is x cubed minus x squared minus 2 divided by the derivation, which was 3x squared minus 2x. And so let's start out here at negative 1.5, positive 1.5, sorry. Positive 1.5, said the wrong number. Okay. There it is. So if I'm here at positive 1.5, I'm at 1.7333. Okay, so x sub 1 is approximately, even though it looks pretty exact, 1.7 with a whole bunch of 3's. Let's plug in 1.7 into our calculator. Okay. Waiting for it to come up. Here it is. And so let me pick 1.7 with a whole bunch of 3's. Waiting for my calculator. Okay, and let's see what I get. So I get 1.69. Actually, let me just make this a little smaller so I can cheat and just write the number. Okay, so this is 1.69668803,419. So let's plug that number into this calculator. Come back. Thank you. It is 1.66. Still waiting for my calculator. Okay, 1.69668803,419. Okay, let's see what I get. Oh, it's almost exactly the same number. So I get x sub 3 1.69, so those are the same, 56 tenths, 100,000, 10,000, not quite. It probably is correct to this value, to the 10th, to, it's probably 1.6956, but I have to go one more just to be sure, 5793. So let's do one more. And so
Professor, the
question.
point of this is to get to a common number that keeps repeating itself.
Yeah, so what you want to do is you want to, so like right here, I know that the first digit is a 1 because they're always ones. Next, notice that it went from a 5 to a 7 to a 6 to a 6. So I imagine the next number is a 6. And then the next number is a 9. And then I don't know what the next number is after that, because I have a 6 here and a 5. If they're always converging to the same number, I know what the number is. So let's put in that number. 1 point. It'll take a second here. 1 point. 6, 9, 5, 6, 2, 1, 6, 5, 9, 3. Okay, and let's see what I get. I bet you it's the same number, or almost the same number. And so I get 1, oops, come back up here for 1 second. I get 1.695, same number, 620, 7695. 6. So I accept these numbers are the same, 1.69562. So it's converging on this number. I don't know about these other digits here, but tenths, hundredths, thousandths, 10,000ths to the 100,000ths. So I definitely know that my answer is approximately 1.6956. And so I've converged to something that's certainly in that realm. Okay, let me do problem number 40.
Can I just ask you a question?
Sure.
The calculator that you were using, is that a special software that?
This is a TI-83. So this is a scientific, this is actually a graphing calculator.
Okay.
Okay. You can always use a regular calculator. The reason to use this calculator is just because it knows how to plug in, it's faster because it remembers the formula. So since it remembers this formula here, then it's faster to use. Okay.
Okay.
And of course, on a take-home exam, you can use things like a graphing calculator as long as you show all your work. And showing all your work was actually what I've shown. So this is all the work that is necessary.
Okay.
To get
Thank
full
you then.
points for a problem like this. That's full credit.
Okay.
Okay.
Thank you.
So theoretically, you're not supposed to use a graphing calculator, but that's really when you're inside a classroom. When you're not inside a classroom, there's no way actually for me to check that you're not using a graphing calculator. So then I allow it, because there's no way to check against it. Okay, problem number 40. If a candy company makes spherical shaped lollipops with radii between 1 centimeter and 4 centimeters, use the intermediate value theorem to determine what will be made with a volume of 200 cubic centimeters. Okay, so I know that a lollipop here, let's say of radius r, let me get another page, has a volume of 4/3 pi r cubed. So it's 4/3 pi r cubed. And so that is the volume of a spherical of a sphere of radius r. And it says, well, the radii are between 1 centimeter and 4. And so I have that the radius is between 1 centimeters. Plug in 1 here. And so if I plug in 1, 4 pi over 3. Note that 4 pi over 3 is approximately 4.188790205. So you can keep that in the back of your mind. And this is 1 and 4 centimeters. And so 4 centimeters will be 4 pi over 3 times 4 cubed. So 4 cubed is 64 times 4 is 256. So my volume is 256 pi over 3, which is approximately it's around 250 is approximately 268.08 25731. Okay, so now we want to see if this is, well, notice that if you start out, you're somewhere around 4. Your volume is somewhere around 4. By the time you get up to 4 centimeters, all of a sudden your volume has increased to 268. And so, since the volume function is a continuous function, so since V is continuous, and it's continuous, obviously, on the closed interval, it's continuous everywhere, but in particular, in the closed interval 1 to 4. And since $200 is between the volumes at the endpoints, then by the intermediate value theorem, we have that there exists I don't know, let's call it R sub 0 in the interval 1 to 4, such that the volume for that particular radius is exactly equal to 200. So yes, by the intermediate value theorem, So by this intermediate value theorem, we can make with a volume of 200 cubic centimeters. And that is your answer. And let me just see, it was cubic centimeters. Yeah, cubic centimeters. Let me do problem number 41. And so, for problem number 41, it says factor the following expression completely on Z2. Oh, okay, so I want to do this on Z2. Well, Z2 is particularly nice because it just says, well, if something is even, make it 0. If something is odd, make it equal to 1. And so I have that x to the 5th plus x to the 4th minus 4x cubed minus 4x squared minus 5x minus 5 is equal to 1x to the 5th plus 1x to the 4th. Well, negative 4x cubed is, well, that's an even number. You could add a multiple of 4, 4 to get 0. Negative 4x squared, well, again, negative 4 is even. So on Z2, this is just equal to 0. Just add 4. Negative 5x, well, that's odd. So this is just going to be plus x. Since I can add 6, which is a multiple of 2, to negative 5 to get 1, and add to this a 6 again. Okay, so let's see if I can factor this. So the first thing to do is just to see if I have some roots. If I have some roots here, so I want to see determine linear factors of this equation on Z2. And so I really want to see, that means I want to determine roots. So look for roots of this equation in Z2. There's only 2 things to check, 0 and 1. So you just have to check 0 and 1 to see if it works. So there's not a whole lot of things to check here. So let's check 1. I have x to the 5th plus x to the 4th plus x plus 1. And so they're an even number, that's going to be 0. Okay, so if you add, you get that it's even, so you know it's 0. So that's good. Oh, what? I didn't write down the coefficients, you jerk. And so this is 1 x to the 5th plus 1 x to the 4th, no x cubed, no x squared, plus 1x plus 1. Okay. Sorry, I was trying to, I want to factor the thing I wrote. Okay, so 5, 4, 3, 2, 1, 0. Drop down the 1 times 1 is 1, plus 1 is 2, but again, 2 mod 2 is 0. 1 times 0 is 1, plus 0 is 1, times 1 is 1, plus 0 is 1, times 1 is 1. But 1 plus 1 is, ooh, this doesn't factor. 1 plus 1 is 2. Okay. 1, 2, 3, 4. That should have worked. 1, 0. Oh, you stupid jerk. If I can multiply my 1, I'm okay, so I obviously made a mistake. 1 times 0 is 0. Plus 0 is 0. Times 1 is 0. Plus 0 is 0. Times 1 is 0. Plus 1 is 1. Times 1 is 1. Plus 1 is 2, which is 0. Good. That works. There are two numbers, so 1 should work again. Okay. Drop down to 1. Times 1 is 1, plus 0 is 1, times 1 is 1, plus 0 is 1, times 1 is 1, plus 0 is 1, times 1 is 1, plus 1 is 0. Good. There's 2 4 numbers. So let's try 1 again. Drop down to 1, times 1 is 1, plus 1 is 2, mod 2 is 0. Times 1 is 0, plus 1 is 1, times 1 is 1, plus 1 is 2, mod 2 is 0. Let's do, again, they're 2 numbers, so that's good. Let's try 1 yet again. Drop down to 1, times 1 is 1, plus 0 is 1, times 1 is 1, plus 1 is 2, mod 2 is 0. And so I get that this factors into, I'm going to have to rewrite it, there's 1, 2, 3, so I get that x to the 5th plus x to the 4th minus 4x cubed minus 4x squared minus 5x minus 5 on Z2 is equal to. So I factored 1, 2, 3, 4 of these. So this is equal to x minus 1 to the 4th, because 1 is a root, times this last reduced equation, which is x plus 1. But if I look at this, well, subtracting 1 is the same as adding 1, since if you negative 1 mod 2 is just positive 1. It's an odd number. So this is x plus 1 to the 4th times x plus 1 is x plus 1 to the 5th. And therefore, I have factored this completely. So it's just x plus 1 to the 5th. Okay, let's do problem number 42. Factor the following expressions completely on Z3. Okay, so let's do that. I think this is the same problem, but I'm just going to do it on Z3. On Z3, I have that this is equal to x to the 5th plus 4th. Let's add 6 to the negative 4 to get plus 2. Let's add 6. And so I get plus 2 x squared, add 6 again. So that's plus 1x, add 6 again, plus 1. So now, oops, I have numbers. I have the coefficients are either 0, 1, or 2. So these are the characteristic numbers or the of Z3 there. And so let's try to factor this. First, let's see if I can factor on Z3. So let's see if I can find a linear root. So x to the fifth, x to the fourth, 2x cubed, 2x squared, 1x, and 1. Okay. Let's try. Let's try 2. So let's see if 2 works. Drop down to 1. Times 2 is going to give you 2. Plus 1 gives you a 3. But again, 3 mod 3 is just 0. And so the remainder after I've divided by 3 is just 0. Times 2 is 0 plus 2 is 2. Times 2 will give me 4, but then 4. So let's write that down. And then 2 plus 1 is just 3. But again, 3 mod 3 is just 0. Okay. Times 2 is 0. Plus 1 is 1. Times 2 is 2. Plus 1 is 3. Mod 3 is just 0. Okay. So I have here that's 0. So x to the fourth plus 2. Oh, actually, I can factor it just doing sort of the normal way of factoring. So notice that I get the following. And let me add another page here. So notice that I get that x to the fifth plus x to the fourth minus 4x cubed minus 4x squared minus 5x minus 5, and this is on Z3 is equal to, well, I have x minus 2, because that's what I found, times x squared plus, I said it is squared, 43210, x to the fourth plus 2x squared plus 1. Okay. First off, if I add 3 to negative 2, I get plus 1. So this is just x plus 1. Next, you know, x to the fourth plus 2x squared plus 1, I can factor that easily. That's just x squared plus 1 squared. And that's just regular factoring. And so, and notice that the middle term 2 is less than 3, so I don't have to do anything fancy with it. And so x squared plus, so the only thing I have to show is that x squared plus 1 doesn't factor. So let's show that this doesn't factor. Let's show that x squared plus 1 is irreducible. Over Z3. And well, to do that, I'll just check 1, 0, 1. So let's check. Does 0 work? No. So that doesn't work. Does 1 work? Maybe I'll keep going. So 1, 0, 1. Does 1 work? 1 times 1 is 1, plus 0 is 1, times 1 is 1, plus 1 is 2. So again, these are not 0. That work. So I've tried 0, 1, and let's try 2. If 2 doesn't work, then it's irreducible because I've tried every number. And so no number is a root. Well, let's drop down to the 1 times 2 is 2 plus 0 is 2 times 2 is 4. And so 4 mod 3 is 1 plus 1. So none of these are equal to 0. And so I have that 0, 1, and 2 are not roots of your polynomial. So 0, 1, and 2 are not roots of my this quadratic. So therefore, this quadratic has no roots. Okay, oh, so I checked the 0, 1, and 2. Okay, so I checked 0, 1, and 2. These are the only members of Z3. None of those are roots to your quadratic. So therefore, the quadratic has no roots. And so this means that the quadratic has no linear factors. Since it has no linear factors, that means that it is irreducible. And so this quadratic is irreducible. The quadratic x squared plus 1 is irreducible. Over Z3. And so that means that I was able to factor x to the 5 plus x to the 4 minus 4x cubed minus 4x squared minus 5x minus 5 to equal x plus 1 times x squared plus 1 squared on Z3. And that's your answer. So I was able to factor it, and I showed that this was irreducible. So it really is the complete factorization that I had surmised was the complete factorization. 43, determine the minimal monic polynomial in Z with the following roots: 2, -5, and I. Well, if I is a root, and if the coefficients are real, they're integers, then I know that its complex conjugate is also a root. So therefore, my polynomial, I don't know, let's call it f of x, is just going to have the form x minus 2 times x minus I times x plus I. Let's simplify this. X minus 2 times x plus 5 is x squared plus 3x minus 10. X minus I times x plus I is just x squared minus I squared, but I squared is -1. So this is plus 1. And so now let's multiply this out. So f of x is equal to, let's multiply by x squared. So that's x squared times x squared is x to the 4th times 3x times x squared is a 3x cubed minus 10x squared plus x squared is minus 9x squared plus 3x minus 10. And that is the polynomial that has the given roots and is monic and is actually of least degree. Let me do problem number 44. Determine whether the polynomial is irreducible over the integers. Well, I have that 3, 7 is an odd number. The leading order coefficient which is really just the leading order coefficient, is 3, which is odd. And let's call this f of x. If I plug in f at 1, well, that's just 3 plus 1 minus 3 plus 5 plus 7. So that's going to be a 10, 16, 13. And so f at 1 is 13, which is an odd number. Therefore, since the constant term was odd, since the leading order coefficient is odd, and since the value at 1 was odd, I know that my polynomial is irreducible. And again, I'm going to call it f of x is irreducible over the rational numbers. And that's it. Let's do problem number 45. Let me do problem number 45. And so I want to determine if the following polynomial is irreducible over the rational numbers. So let's see if I can use Eisenstein's criteria. So let's try 2. And so notice that 2 does not divide 1. The coefficient of x cubed. It does divide the coefficient of x squared and the coefficient of x and the coefficient of the constant term, and 2 squared does not divide 2. Therefore, by Eisenstein's criteria, we have that this polynomial is irreducible over the rational numbers. And that's what we wanted to show. Let me do problem number 46. Solve the following equation for x in the field of rational numbers, given that one root is negative of the other root of another root of the equation. So let a be a root. Then negative a is another root. And let's call the other root b. Of this polynomial. Then I have that 9x cubed plus 45x squared minus 4x minus 20 is equal to 9 times x minus a, x plus a times x minus b. And so this is equal to 9 x minus a times x plus a is x squared minus a squared. Let me get some additional space here to work. So this is equal to 9. Let's multiply. So it's x cubed plus bx squared minus a squared x minus a squared b. Okay. And so this is equal to 9x cubed plus 9bx squared minus 9a squared x minus 9a squared b. So let's equate coefficients. So 9 is equal to 9. That doesn't really give me anything. So sure, that's a true statement. 45 is equal to 9b equal to 5. I have that negative 9a squared is equal to negative 4. So that says that is equal to 4 over 9. And so A is equal to plus or minus 2/3. It really doesn't matter which I choose because the other root is going to be the negative of it. Notice that the last 9a squared b equals negative 20 still works. And so, let me add another page. My solution to this equation is x is equal to plus or minus 2/3 and x is equal to negative 5. Is equal to positive 5. And that is your answer. Okay, let's do the next problem. So problem number 47. Okay. So problem 47. The space available for the installation of 3 solar collecting panels requires that their lengths differ by amounts shown in the illustration and that the total of their widths be 15 meters. To be equally effective, each panel must measure exactly 60 square meters. Find the dimension of each panel. Okay, so let's call the length of this guy x. Okay, so I have to have that the area of a rectangle is length times width. And so that says that the length is just equal to the area over the width. Okay. So the area of the first one is 60 and the width is x. The area of the second is 60 And well, the width is 2 meters longer, so it's x plus 2. And lastly, the length of the last one is, well, the area is 60, and the width is going to be x plus, well, 2 plus another additional 3 is 5 additional meters, so x plus 5. And I have to have that the sum of these 3 lengths is 15. So the sum of those is 15. Let's simplify this. So I can divide by 15. That will get rid of the 60 divided by 15 is 4. And then I can multiply by x plus 2, and x plus 5 to get rid of all the denominators. And so if I do that, the 60 divided by 15 is 4. The x's cancel, so you get x plus 2, x plus 5. 60 divided by 15 is 4. The x plus 2's cancel, so you get 4x, x plus 5. 60 divided by 15 is 4. The x plus 5's cancel, so you get must equal. The 15's cancel, so you get x times, well, x plus 2 times x plus 5 is x squared plus 7x plus 10. So let's simplify this. Let me move this a little over so I can put the 10. Okay. So let's simplify this. So this becomes 4. Well, this is again the x squared plus 7x plus 10. So this is 4x squared plus 28x plus 40. Let's multiply 4x inside the parentheses. So it's 4x squared plus 20x. Let's multiply the 4x inside the parentheses. 4x squared plus 8x equals, multiply the x inside the parentheses, x cubed plus 7x squared plus 10x. And so let me insert one last page. So this is equal to x cubed. Well, actually, let's add up all the x squares first. So I get 12x squared, combine like terms. 28x plus 20x plus 8x is 56x plus 40 equals x cubed plus 7x squared plus 10x. So now let's subtract 12x squared from both sides of my equation, 56x from both sides of my equation, 40 from both sides of my equation. Okay. And so let's try to solve this, and let's try to find some rational roots. Yeah, they don't say that they have to be rational, but let's at least try to find first some rational roots if possible. So let's find the factors of 40. 1, 2, 4, 5, 8, 10, 20, 40. Next, let's find the factors of 1. Well, that's just going to be plus or minus 1. So P divided by Q. So the possible rational roots. P divided by q are plus or minus 1, plus or minus 2, 4, 5, 8, 10, 20, 40. Okay, so let's try to solve this. So I have here that's a 46. Okay, just alternate signs. Okay, so I have 1 minus 5 minus 46 minus 40. So if I change the signs of these two, this is 46 minus 1 is 45, minus 45 is 0. So let's try negative 1. Let's see if that works. Drop down the 1 times negative 1 is negative 1. Minus 5 is negative 6 times negative 1 is positive 6. Minus 46 is negative 40 times negative 1 is a positive 40. Minus 40 is 0. Okay. Let's try maybe 10. Let's try 10. See if that works. 1 times 10 is 10. Minus 6 is a negative 4. A positive 4, sorry. Times 10 is 40. Minus 40 is 0. And lastly, let's try negative 4. So drop down the 1 times negative 4 is negative 4. Plus 4 is 0. Okay, so the possible rational roots are, the roots of this equation are negative 1, negative 4. Okay, so since this is physical and we have here a length, I'm going to get rid of x's that are negative. So I'm going to get rid of these negatives just because they're not physical. And so I want to determine the dimensions of each panel. So this is going to be a 4. This will be a 10. And well, 10 times 6 is 60. So it's a 10 by 6. So this becomes a 10, meters by 6 meters. That's one of the panels. Then the next panel is going to be a length of 2 more. So 10 plus 2 is 12 meters. 12 times 5 is 60. You could also do it 60 divided by 12 is 5. And lastly, let's go an additional 3 meters. That makes 15 meters. 60 divided by 15 is 4 meters. And so these are the dimensions of, well, it's the 3 panels. And that's it. Let me do problem 48. Solve the following equation for x in the complex field. Given that 2 roots are complex conjugates whose product is 9. Okay, so let's do that. And so let's call it A plus BI be a root. then a minus bi is also root. Under the condition that the product, sorry about that, that the product of these two roots is 9. Therefore, a squared plus b squared must equal 9. And let, oh, I don't know, let c be another root. And let d be another root. Then we have the following. Okay. Let me add another page. I'm waiting for it to move. Okay, let's add a page. I'm inserting a page. Insert page. Please insert page. Okay, and so I've inserted my new page. So I have that x to the 4th plus x cubed plus 3x squared plus 9x minus 54 is equal to x minus a. Oh, come on. X minus a minus bi minus bi. So x minus a minus bi times x complex conjugate minus a plus bi times x minus c times x minus d. Okay. So let's multiply this out. Actually, maybe I should, since it's gone to the next page, maybe I'll just say that this is equal to this. Let's multiply this out. And so this is just equal to x minus a squared minus b squared I squared. So that becomes plus b squared times, let's multiply out x minus c times x minus d. So that's x squared minus c plus dx plus cd. Let's simplify this. So this is equal to x squared minus 2ax plus a squared plus b squared times x squared minus c plus dx plus cd. Well, I know that a squared plus b squared is just 9. So this is x squared minus 2x plus 9 times x squared minus c x minus dx plus cd. So let's multiply these two together. And so I get x to the 4th I get minus C, I'm going to group all these x cubes together. So minus C x cubed minus D x cubed minus 2a x cubed. So those are all the x cubed terms. Now let's do the x squared terms. So I have CD x squared I have plus 2ac x. I have plus 2a dx of plus 9x squared. Okay. Next, let's do the x terms. And so I have minus 2a cd minus 9cx minus 9dx. And then lastly, plus 9cd. And so let's equate coefficients. And so the x to the 4 terms don't give you anything, but for the x cubed term, I get that minus c minus d order minus 2a minus c minus d is 1. I have that let's write this as 2ac plus 2ad plus cd is equal to 3. Next, let's get another line. Okay, so next equation, R3. I have the x terms, CD, and so I have 2ac plus 2ad plus cd plus 9 is equal to 9. Okay. That's the x. Oops. That is the x squared term. Oh, wait. So wait, 1 second. So x cubed was 1. X squared was 3. Oh, x squared. I wrote something wrong for the x squared. Somehow I went, so this was the x squared term. So x squared, and now let's do the next term. So it's I wrote something wrong. So this is a minus 2acd minus 9c minus 9d is equal to the x term, which is 9. And lastly, I have that the very last term, 9cd, is equal to negative 54. Okay. I can at least simplify some of the CD terms, but so from R4, I get the following. So from R4, I get that D is equal to negative 54 over 9C, which is a negative 6. And so let me simplify. And so let's look at this. So let's look at R1, I guess. Okay, so okay, so if I look here, sorry about that. So if I look here at R1, and I look at R3, simplifying this guy, we'll make it something that looks the same as this guy. Okay, so let's multiply, by negative 9. Yes, let's multiply this guy by negative 9. So negative 9 R1 becomes 18A plus 9C plus 9D equals, and let's look at R3. Hello? No, just getting something. Okay, so let's look at R3, which is a negative 2A times CD. And so maybe I should have just said that CD, dividing both sides of my equation by 9, negative 6. And so let's make that negative 6 plus minus 9C minus 9D equals 9. And so I get that the 9C's, 9D's cancel. 18A plus 12A, negative 2 times negative 6 is 12. 12A plus 18A is equal to 0. So I have that A is 0. So that's good. Thus simplify my life quite a bit. And so, given that, given that A is 0, let's see how that simplifies life. And so, R1 then just becomes C plus D is -1. R2 becomes CD equals -6. So that doesn't really tell me anything. So CD equals -6, which is what I had from before. Actually, I can now solve for C and D. Next, since A is 0, this says that -9C plus minus 9D is 9, so C plus D is -1. So that, again, that doesn't. R sub 3 becomes -9C minus 9D is equal to 9, which is the same as, so that doesn't give us anything. And the fourth equation just says that 9CD is equal to -54 with the same second equation. So I get rid of the third and fourth equation. And so I have that D from R2 I have that D is equal to -6 over C. Let's plug that into R1. And so I have C minus D is equal to -1. Let's multiply by C. And so I get C squared minus 6 equals -C. And so I have C squared minus C minus 6 is 0. So let's factor this. So this is just C minus 3 times C plus 2 is 0. So C is equal to, C minus 3 is equal to 0. Or C plus 2 is 0. So C is equal to 3. C is equal to -2. And so let's figure out lastly, what D is. And so D is equal to -6 divided by 3, -2. Or D is equal to -6 divided by -2, which is 3, meaning they're interchanged. So the roots of my equation are A, 0, plus or minus. Oh, and I guess I should say that since A is 0, then B squared, I should have said that. So since A is 0, that implies that B squared is 9. And so B is equal to plus or minus 3. So I get that my solutions are 0 plus or minus 3i, and then 3 and -2. And that is a solution to my equation. So problem number 49. So we're almost done. Solve the equation for x in R, given that one root is the negative of another root, and the other two roots form conjugate pairs. So let one root be A, then the other root minus A is a root, and let's say B plus rad C be a root, then B minus rad C is also a root. Okay, so I have that x to the 4 minus 2x cubed minus 8x squared plus 8x plus 16 is equal to x minus a times x plus a times x minus b minus rad c times x minus b plus rad c. And so this is equal to x squared minus a squared. This is equal to x minus b squared minus rad c squared. Let's multiply this out. So this is equal to x squared minus a squared times x squared minus 2bx plus b squared minus c. Let's multiply this out. So this is equal to x to the 4th plus, let's do x cubed. There's only one x cubed term, minus 2bx cubed. Let's do the x squared term. Minus a plus b squared x squared minus c x squared. Let's do, so minus a squared times minus 2bx is a plus 2b 2a squared b x. Plus the last term, the constant term, minus a squared times b squared minus a squared times c times negative c. So it's a plus a squared c. So let's equate coefficients. So, well, 1 x to the 4th is equal to 1 x to the 4th, so that doesn't give us anything. So I have that equating the x cubed terms, I have negative 2b is equal to negative 2. So that says that b is equal to 1. Next, I have that negative a squared plus b squared minus c is equal to the x squared term, which is negative 8. Since b squared is, since b is equal to 1, then b squared is equal to 1. So I have a negative a squared plus 1 minus c is equal to negative 8. Let me insert. And so negative a squared minus c minus 9. Negate everything, so I get a squared plus c is equal to 9. And so, let's call this R1. So I have one equation here. Next, I have that 2a squared b, and that's the x term, is equal to 8. And so I have that a squared b is equal to 8. Let's call that R2. Oh, and of course, b is 1. And so I have that a squared is equal to 4. Therefore, a is equal to plus or minus 2. And so R1 then says that 4 plus c is 9. So c is equal to 5. Okay, so from there, I get that x is equal to a, which could be either plus or minus 2, and then minus a, so that gives me both of them. And then b plus or minus rad c plus or minus rad 5. And that is my solution. Okay, so finally, problem 50. It's the last problem. Solve the following equation for x in the field of complex numbers, given that one root is the negative of another root, and that two other roots form complex conjugate pairs whose product is 16. So we're going to be using these automorphisms to solve this equation. 3x to the fifth minus x to the fourth plus 36x to the third minus 12x squared minus 192x plus 64 equals 0. So first, let a be a root, and negative a is then a root, since you have that one root and it's negative is a root. B plus ci be a root. Since two of the roots are in conjugate pairs, b minus ci is a root also. And we also have that b squared plus c squared is equal to 16. Lastly, so that gives you 4 of the roots. Lastly, let d be a root. And so that gives you all 5 roots. So now I have that 3x to the 5th minus x to the 4th plus 36x cubed minus 12x squared minus 192x plus 64. Let's suppose that I can factor this. And so we've been given the splitting field. I have a 3 out in front. That's the leading order coefficient. So let's write the leading order coefficient. I have that a minus a roots. I have that b plus ci, b minus ci, roots, and d is a root. So now let's multiply this out. First off, I had the product, the sum and difference, and so this difference of squares, x squared minus a squared. And similarly, this is the sum and difference of the difference of squares. Ci squared, well, minus the I squared. I squared is negative 1, so that negative becomes positive. It's plus c squared times x minus t. So this is equal to, let's multiply this out. First off, let me multiply x squared minus a squared times x minus d. And so let's first multiply each of these by x squared. So I get x cubed minus dx squared. Let's multiply each of these by minus a squared. So you get minus a squared x plus a squared d. This is, again, a special product formula. This is just the perfect square. And so I get x squared minus 2bx plus b squared plus c squared. So this is equal to, well, let me multiply the 3 inside the parentheses and use the fact that b squared plus c squared is equal to 16. So I have x cubed minus dx squared minus a squared x plus a squared d times, again, let's multiply 3 inside the parentheses. And so I get 3x squared minus 6bx. Again, b squared plus c squared is 16. 3 times 16 is 48. Now let's multiply this out. And so I have x cubed times 3 squared is 3x to the 5th. I have x cubed times negative 6 bx is negative 6 x cubed, x to the 4th. I have negative d times 3 negative dx squared times 3x squared is negative 3 bx to the 4th. I have x cubed times 48 is 48x cubed. I have negative d times negative 6, but negative negative dx squared times negative gives me a positive 6 bdx cubed. I have negative negative a squared x times 3x squared. And so that gives me minus 3 a squared x cubed. Now let's do the x squared terms. So I have a squared d times 3x squared is 3a squared d. I have minus a squared x times minus 6bx. So that gives me a plus 6a squared bx squared. I have negative dx squared times 48 gives me a negative 48 x, negative 48 d x squared. I have a d squared. Let me say that again. I have a squared d times negative 6b x. That gives me a negative 6a squared bd. I have negative a squared x times 48. That gives me a negative 48 a squared x. And lastly, a squared d times 48 is 48 a squared d. So, equating coefficients, I have, well, 3x to the fifth is 3. 3 is equal to 3, so that doesn't give me anything. But this negative 6b minus negative 6d. Oh, wait, 1 second. That's a d. That b is a d, isn't it? This is x to the fourth. So that's a negative 6bx to the fourth, but then that's a negative d times 3 is a negative 3d. So I wrote that wrong. So a negative 6b minus 3d is a negative 1. So that'll give me in my first equation. So my first equation, negative 6b minus 3d is negative 1. Second equation. So that was for the x to the fourth term, x to the third term. 48 6bd minus 3a squared. So that's equal to the x cubed term, which is 36. Next equation. For the x squared term, I have 3a squared d plus 6a squared b minus 48d is equal to negative 12. I have the fourth equation. And so my fourth equation is minus 6 a squared bd minus 48 a squared. So the coefficient of x is negative 192. And we have, lastly, fifth equation, that the constant term, 48 a squared d is equal to our constant, which is a 64. And lastly, we were also given the fact that the product of the complex roots was 16. So we had that b squared plus c squared is 16. Okay, so we have these 6 equations. So let's look at the fifth equation here. So r sub 5. Let me simplify this. And so let's divide both sides of my equation by 48. D is equal to, well, 64 over 48, which is the same as 4/3. So this is equal to 4/3. Let's call this S1. So a new set of equations. Okay, so now let's plug this into, I have a squared d here. So let's simplify this. So let's substitute S1 into S4, into R4. Okay, so if I do that, I get negative 6 b times a squared d, which is 4/3, minus 48 a squared equals a negative 192. Okay. 6 divided by 3 is 2. Times 4 is 8, so I have a negative 8. B minus 48 a squared equals negative 192. Let me look at R2. And so if I subtract 48 from both sides, I just have that 6bd minus 3 a squared is equal to a negative 12. And so if I take that and multiply it by negative 16, I get negative 96 b plus 48a squared equals 192. Let's add these. So if I do that, I get negative 96b. Oh, I forgot to write the d. That was a BD. That was a BD term here. So negative 96 BD minus 8B is equal to, since the 48 8 squares and the 192s cancel, 0. Let me multiply this by a squared. Okay, and so I get negative 96 b times a squared d, but a squared d I know is 4/3. minus 8a squared b, okay, is equal to 0. And so I get 96 divided, which is 32 times 4, which is 128 b minus 8a squared b equals 0. Let me factor this. And so let me factor out a negative 8b. So what remains is, well, let's 128 divided by 8 is just 16 plus a squared, 0. Since I'm assuming that a is real, that was one of the assumptions, that was one of the conditions that they gave us, is that a was a real number, then I can't have that 16 plus a squared is 0. Therefore, negative 8b must be 0, so b is equal to 0. Maybe I'll call that S2. Now, I have that R6. Well, let's plug that into R6. So let's plug S2 into R6. So I get 0 squared plus c squared is 16. Therefore, c is equal to plus or minus 4. Now, it doesn't matter if I pick c to be plus 4 or minus 4, because its negative is also root. So let's just say, let's c equal positive 4. Let's call that S3. Okay. And so now, let's look at R4. So let's look here at R4. So letting b equals 0 in R4, we get, well, since b is 0, this first term is 0, so I just have that negative 48 a squared equals negative 192. Therefore, divide both sides of the equation by negative 48. So a squared is equal to 4. Therefore, a is equal to plus or minus 2. Again, since these came in complex conjugate pairs, actually, well, this was one, but that was in complex conjugate pairs. Since this one had that one was root was positive, the other was negative, I can just take this to be positive 2. And so let's call it S4. So I have A, B, C. Let's figure out D. So again, let's use the fact that use R1. And so that B equals 0 in R1 just gives you that negative 3D is negative 1. And so D is equal to 1/3. And so finally, that means that, well, I have all my roots. So A is 2. So one root is 2. The other is negative 2. And C is 4. So I have 0 plus or minus 4, 4i. So I have a negative 4i and a positive 4i. And lastly, d is 1/3 are the solutions to my equation. And so that finishes off the review.